All right, looks pretty good. So we're ready to start this. So what we need to do, basically, is start to get a sense for how we. Oh, okay. Let's get oriented here. All right. So this thing can move out like this, and it can also move this way. And there isn't a limit there. We need to add a limit there somehow, but I don't really care yet. And I think there's not a limit all the way there. Yeah, so it's weird. It was weird because I catted the rail in a different. All right, it's not important. But so the goal here is, and I want to actually try to do this. I want to do this without referring too much to other people's designs because I kind of want a challenge. And the z-axis is gonna be, I think, the hardest part of this. Actually, though, I want to do something just a little goofy and silly to start us off. You know, something a little silly, a little goofy, a little goof and a gaff, and I want to start to get appearance. How do I change the appearance of something? If I go to this assembly, that didn't even work. All right, if I take this part, I'm gonna take this rail, properties, um, is it in property? See, the thing is, I think that, oh, this is a linked document. So, okay, let's try to get like this, for instance. This is a part that definitely lives in here. So we have this, we have this rod, and go to properties. Still, it doesn't seem anything happens. Why? Is there really no appearance in this? Is it only in All right, let's try to change the color of the carriage. Why is it taking so long? Um, what the hell is going on here? Okay. What is happening? All right, there we go. I don't know what's going on. So if we take, I don't know, this body, assign material. Okay, so they do have a material library. And let's see if they have PLA. I'm actually so curious. Dude, it's so weird. Wait, hold on. It's so weird. Like, why? Oh, there they go. There you go. It's just a bad search algorithm. So should we just assign all this stuff? I mean, I guess so. I don't know what that. I guess that gives us mainly like moment of inertia type stuff. Um. Anyways, let's go to appearance. Okay, so and this is just color picker. Okay. So what that means is that then we need to. That's kind of annoying, right? Because then it means that if we wanted to change the rail, for instance. Um. So these rails, we got it. We can just open this up, right? Switch to rod. And then we just change the appearance of this rod. Edit appearance. It's like kind of like an aluminum, right? Kind of like a light aluminum color. It's not white, but it's maybe it's like that. Anyways, so okay, so now if we go back to there, is it gonna update? You'd kind of hope it. Oh, there you go. Okay, so it did update. So this part, the pulley. So if we go, the thing is, it is a little bit weird that I don't know. I guess it's just a design decision on their part. Is that um this is gonna be like aluminum. I know that there's yeah, stainless steel, aluminum. See, they just have. I mean, the thing is, isn't aluminum almost always alloyed, or at least I don't know anything about the material science of this stuff. So let's just do this. it's almost certainly aluminum. I don't think I have one sitting around here. Or I probably do, but I don't want to find it. My table has gotten to be a total mess again. Uh, okay, so we have that, and then we want the appearance to be like this. Honestly, that. Okay, great. So then now all the pulley wheels should be colored a little bit better. Because all right. So this is starting to get kind of nice. But so we got to switch to. We got to switch to assembly 1. Great. And then we got to take this rail, open that document. I guess we do want to open that document, right? Options. Allow pop-ups from CAD.OnShape. So we just want to take this, and this is not like this is going to be a darker properties. Why can't I change the wait, versions are view only, return to main. Okay, here we go. So now I don't know. We probably do want to make it steel, but I can't imagine that I'm going to. Yeah, let's make it like that. And then the carriage, the carriage is like green and like something else. But I think we got most of it. Right. This is starting to look. Oh wait, we gotta do a version, right? So we have to like so this should be updated now. And then we need to make a version. And I don't remember how to do that. Oh, I think it's just this. Create version, color the rail. Okay, so now we do this, and then we can yeah, pull the changes. So we update all. Great. And then this should okay, great. Cool. So this is starting to look so now all these parts except for this, the blue is all 3D printed parts. I'm pretty sure. Yeah, so that's good. Okay, now it's time to do the actual work here. So I think we're going to take just a standard Sharpie. We're just going to use a normal Sharpie to start with. So I'm going to go to GrabCAD. And I'm just going to look up like GrabCAD. Wait, GrabCAD is a public company? Huh. I guess they got bought. Oh, didn't Stratasys sue Bamboo? I'm pretty sure that's true. All right, anyways, yeah, that seems good. It's so annoying that they make you freaking log in, dude. So stupid. Ugh, and I don't have the. Ay. Okay. Wait, actually, wait. Hold on. I'm dumb. No, I think it's. Oh. Ugh. GrabCAD sucks. Hold on. Give me a second. I'm sorry. I have to go to Chrome, and I can't show Chrome. It's kind of a hard rule that I have. Okay. So, um, so how do we want this thing to work? We have this rectangular prism thing, right? Um, let's just do the side view. So let's see if we were to go normal to this. What is this sketch gonna look like? I'm thinking of doing it on the outside. So we're gonna have a bracket. I mean, the thing is, it's kind of an interesting decision on whether or not you choose to bracket or you choose to just redesign this part. I feel like there's enough features in this thing that I just want to make a new part. So, all right, so we made that call. We're making a new part, and it's going to sit over this thing like an L. Okay, it's going to sit over like an L. There's going to be a bolt in here. It goes in like this. And then there's going to be some ring thing where you put the pen in. You press it down, and then you have like a thumb hand tightening bolt that you just tighten it down. So that's going to be the first iteration. And then the next step is that we need that whole assembly that was once bolted down to be able to be lifted by. And the thing is, this is where this whole thing gets a little confusing because I ideally would use a stepper motor. But the thing that's crazy about the stepper motors, one, it's that I got totally boned on these things that for some reason have like 6 pins on them. And the cables that I got are like in the wrong order. So I don't know, just kind of a pain, but it's not a big deal. The main thing is that, okay, so let's I say we just get catting. So what is the so okay, so I guess what we need to know right off the bat is the distance maybe from the bottom of this to the ground. So that's actually quite high. So if we're to take the length of a Sharpie, so let's I guess we just want to insert, import, downloads, Sharpie. Oh shoot. Wait. Does that work? I don't really want to do that. I kind of want to just unzip this. Okay, it's just okay, but this should work. Import appearances, import material density. Okay. Seems good. It's just a part, so that seems fine. And it's just called Sharpie. Nice. Okay, that's great. I will do a couple of dimensions. Let's see if I can find a caliper. Okay, so the calipers will just be, we're just going to take a couple of measurements to make sure that we are doing the right thing. So I don't think that there's a taper here, but I am going to do it right below the cap. We're getting 12.3. So what I'm going to do is take this, and we're getting 12.3. Okay, wait, was that? Or I was getting 1.3. It's close enough, though. Should be close enough. Given that we know we're going to do... So our first model is just going to be an etch-a-sketch type of thing. It does taper, though, because it becomes 10 at the top. So I kind of want to check. 11, yeah. There is a taper to it. You know what would be cool is if Sharpie really released their own CAD. It'd be kind of fun. 10.5. Okay, so what we want to know now is we want to take this surface, I guess. I don't know how this is going to work. I'm going to take this circle. Okay, cool. We have a center distance. And the length of this whole thing is going to be 125 millimeters. Yeah, it's close enough. So now the question is basically we measured, so then let's just say this is the ground. We measured the distance between here as like 70. .920. Okay, so that means that the pen, there's a pen. Here's the pen. And I'm just sketching this out. This distance is, what did we say? I don't like that it gets rid of my measurements. .125.45. Okay, so that means that okay. So I think I'm ready. We're gonna do a new part. And actually, I'm always so bad about this, but deciding whether or not to do the new part on the but okay, so let's do it. So this is the Y rod holder, but then there's the Y rod holder right, and I'm pretty sure that this is the one. So this is like closer to the middle, and I'm pretty sure. So let's just make sure we always keep this in a new browser tab, and we can I'm almost positive that this is Y rod holder. Wait, really? Y rod holder, Y rod holder. Is that the wrong part? No, it's definitely a different part. Oh, yeah. Okay, wait, hold on. We need to rename this to be... Okay, cool. Yeah, I was a little confused for a second, but it's all good. All right, so what I want to do is I want to go... I wish Switch 2 was actually an open in new browser tab. I guess we have it open. Okay, so what we're going to do is we're going to sketch on here. Let's get rid of these planes. And I just want... It's just going to be a flat plate, and what I'm kind of... So I guess... So wait, but this is a threaded insert hole. So what we actually want to do is we want to sketch on here. We want to make a circle that's concentric with this, but actually M... Oh, that's so annoying. This is going to be M3 hole. So we're actually going to extrude this so it's a little bit snugger because that's kind of what you want. Why am I not getting this? Oh, wait, was I? Hold on, let's undo. There we go. All right, so what we're going to do is we're going to take this, this, and this. And we're just going to extrude it by... And I'm just going to say wall because it really... But the thing is, what we want to do is we want to do a new part. Right, so this is a new part right now. And honestly, what I'm thinking is like... It's so weird coming up with this stuff because like... All right, so let's say... So where do we actually want it? That's kind of a good question, right? Do we want to put it in the middle? That's kind of my default thought, but then maybe we want to put it... I think just let's do it in the middle. So let's just... So wait, before we actually do this extrusion, I kind of want to take this sketch, and I just want to keep editing this. So what is this sketch? I don't know what this is. But this... Okay, the stupidest thing that I'm thinking of is just like you draw a rectangle like, I don't know, like this. a rectangle like this. And then you, I don't know, let's see. So we want this to be like 13. So then this one needs to be way bigger than that. Let's say the distance between here is... Oh, it's so stupid. Oh my gosh. This thing is so bad. Okay. But then the thumb screw, then we need a thumb screw thing. Okay, so let's just wait, what is a coincident constraint cannot be applied to... Oh. All right, so can we just take a look at what that looks like? Wait, what is not right about all this? Oh, I can make this longer or shorter. Oh, I can also make this the same thing. Well, that's interesting. I mean, really, it really could just be like that without those rectangles, right? So how would that look? Because I think this and this need to be coincident. So you can't do that. But what about a tangency thing? Can you say tangent? Okay, so you can. So we kind of don't need those rectangles. Those rectangles are kind of stupid. So what we're going to do is we're just going to basically try to delete all of this geometry. Can we? Okay. Delete, delete, delete. Okay, so what we want to do is we just want to do 2 circles. So this one is 13. Let's get our variable studio open though. Should we call this bunghole for, you know, because you have to put whatever. All right. Okay, so this should be okay, and then the distance, and then it really doesn't matter, right? This and this are tangent. That point, do we get a point there? We should, I mean, there is a point at which that tangency occurs, but we don't get a point there. It's kind of annoying. I guess we could do this. And now we have the tangency point. So then what we could say is this and this are now midpointed. We have that now. And then the distance between this and this, I'm just going to make it 3. I'm just going to make it kind of thick. 2, 3. Kind of a big boy. Anyway, so we've done this. Now we can take this, this, and this, and extrude it by wall. Oh, we have to undo this new part. Okay, great. But what we actually have to do, though, is we kind of go back to this extrusion. We're going to undo this. Then we're going to go back to this sketch, and we're going to take this, and we're going to extrude it by, I don't know, yeah, like 25. New add to merge scope part 2. That's not going to work. Why doesn't that work? We're taking this sketch. This is going to be kind of a weird part to print, right? How is that going to get printed? Because alternatively, we could actually just let's try to just sketch out an alternative idea. I don't know. This is all spitballing here. But wait, did we get the center? Okay. So, I don't know. Let's see. I don't know. Who really cares? We're just trying to get, yeah, like 3. And then, so we have this plate, and then we want to draw a sketch on here. Or I guess, yeah, that's kind of the way to do it. But okay, well, in any case, we're going to draw a circle and another circle. Distance these to be 3. Distance this to be 13. Oh, wow, good guess. Okay, then make this and this tangent. Then the line between this and this point and this whole line are midpointed, so that we have that. So then now this is a closed, this is good. So now what we want to do is we want to take this and we want to extrude this. Flip the direction for sure. Oh, you know why? Because I think it's because it's disjoint. I think what you have to do when you do this is you have to take this, and then you extrude it. And yeah, right. See that? So now you get that whole thing. So you flip the direction, then you go up to next. That doesn't work. You have to do up to face. And then I guess the face has to have a constraint on it. Okay, so now you have this. So what I'm thinking is that then you just put like 2 holes here, and then you go up to here and you make this just bigger. I don't know. I mean, it's sketch. What is the dimension here? Oh, what the hell? So let's make it like, so if it's going to be 13 plus 6, that's 19 and it's going to be hard to get in there. So you probably want to make this actually like pretty big, like 30. And then this really only needs to be like 25. So it's kind of like a different shape than I originally thought. So now what you can do is you can sketch on here. Okay, well, you can make a mid-plane. I'll make a plane. I kind of like this part better because it's smaller. It's kind of easier to print. And I honestly, I don't know. It means that we'll have to redesign. We'll have to add a couple of things there. But I like this design way, way more because it's so simple. Let's see, what height did we pick for this? I think it was somewhat arbitrary. Ooh. 20. That's 20. Okay. So why don't we just make it 20? Sipping on promethazine. Yeah, I kind of want to make this even bigger because if you take, let's just like sketch on here, use this, use this. Do we get that line? I guess we do get that line. See, that's nice. Now, if we took the distance from here to here, 5.5, it's not really enough for an M3. I mean, it kind of is. We only need 2. I was thinking 4, but 4 is so overkill, it's crazy. Um... All right, so we're gonna make it. I'm trying to think. The outer diameter of this is 19. Let's just do the math there to get 5.5. So it's gonna be. So this line is going to be 19, and then this thing is going to be 30. I said. So yeah, so that's 11 over 2. Okay. So, and what we want it to be is probably 7. I don't know. This is one of those things where it's like generative design would be so useful where it's just like, what's the right size here? I don't know what the right size is. Someone tell me. But let's just say it's 7. So that means that we're going to have x minus 19 over 2 is equal to 7. Ah, ah. Why doesn't it just give me the solution? So it's 33. So let's just make it 35. So that means that we go to this sketch and make this 35. Great. Now we're going to make that plane, right? Do I have, what is this sketch? What is this? Oh yeah, we can just delete that. Okay. I like that it defaulted to mid. So what, actually a big strategy in Onshape is just select what you need first and then it does some of the inference for you. All right, so we're going to sketch on here. And I guess we have this point. Oh, wait, let's see. This is going to be... We can make it further out. We can make it the midpoint of not that point, but what just happened? L Q line line line. Ugh. I need another line. Okay, there we go. Line. Ugh. Let's get another construction line from here to there, and then we get the distance between this and this, 2.3. Or actually, we don't want that. We want the distance between here and here, 4. Or actually, we do want the distance between here and here. So if I were to draw, do I have M3? No, I don't have M3 socket head. Damn. M3 socket head diam. I think it's like 5.1 or something. It's like 5.4. Might as well make a freaking variable for it. What? Oh, it's because is that a comma? Okay. Great. So wait, where was I? So this, oops. Great. So if we look at the normal here, we shouldn't have an interference, so we should be able to take this out then. Remove up to next. Okay, then mirror that over. It's not it's a feature mirror, it's this extrude, and it's over this plane. Plane, oh. Great. Okay, so now all we have to do is we need to make a, and I'm kind of wondering, so there's sort of two options here. And I think I know which one I want to do. So let's look at what threaded inserts we have. Because the wall thickness I chose was 3. I remember that. So we need something with a depth of 3. By 2, 4, 2.5 by 4. Let's do the M3 by 4. So let's just make the wall thickness a little bit more. So we're going to go to, it's not this sketch, but this sketch will need to be changed. It's this sketch, and this needs to be 4. Great, but the problem now is that it's going to be can we look at this sketch again? I guess it's fine. I mean, there's room for this. Yeah, I think it's fine. So now what we want to do is we want to make a, so we want to select this, and then we want to make a plane. And assuming it's a tangent plane, but then see, that's the problem, is select an additional point. I guess we want this point, right? Okay, great. That works. Let's sketch on here. Then we want to take this midpoint and we want to do a circle. And this is going to be, damn, why do I keep closing this thing when I need it? Need it. So M3 by 4 by 5. So this needs to be, and I'm going to make the clearance actually even tighter. So it's going to be 5 minus 0.3. And we're going to extrude this. And we can't do freaking up to next, right? If we flip, remove, up to next. See, up to next doesn't work, but up to face does work. But that's okay. That's just how this thing works. Great. And now we just need to design. Well, I'll just use a normal bolt. I think I'll just use a normal bolt. So we'll put a threaded insert in there. That'll keep it from moving in and out, so it'll stay tight. And it's 0.3 compression, so it should be a relatively good fit. So now all we need to do is modify the, so let's name everything. So what is this? This is going to be just pen holder. So rename pen holder. I don't know why I moved it over here. It doesn't really make any sense. pen holder. And now we just need to modify this part to have 2 threaded inserts in them. Threaded inserts are so convenient. And you kind of always need a little. It makes the need for a little soldering iron and more, but it does make assembly so convenient. All right, so let's switch to this. We're gonna need to know the center hole distance, but that's okay. Switch to. Okay, great. And now we need to make sure we get the right size. So we can delete this part. We can remove both of these. These are both stupid ideas. Oh, uh-oh. Whoa-oh. How come I can't undo this? It's probably because I'm like in an active editing. Where is it even open? Wait, I'm getting poor connection. What the hell? That don't make no sense. What the hell? Can we just roll this back? I say delete these features. Okay, I guess it's good now. Okay, so we need to now we need to basically just do 2 circles. They're equal. The distance apart from them is going to be 28. Okay, then the line between them is a construction line, and then we're gonna get that midpoint and this point, and then do this midpoint. Oops. Oh, well, that's goofy AF. Let's just make the distance of this like 10, just to fix it. Oh, 10 is right. Let's just make it 20/2. All right. So then so wait, what's missing here? Oh. Okay. So that's good. So now we just need to dimension this. And this is going to be also 5 minus 0.3. And we're just going to do this, extrude this, and this is going to be, yeah, we made this M3 hole, right? Yeah, 3.4. So that works out. So now we need to remove, and we need to remove how much? And this shouldn't collide. Yeah, so this is not going to collide with the rod. So we're good on that front. So this just needs to go in, I think 4. Yeah. Great. So we put the threaded inserts in there. So now let's go to this, and we're going to insert our pen holder. So this is the first iteration of this whole thing. I like this more than the other thing of using the holes. I mean, it means we have to reprint it, but it's also like kind of nice. So this will work, but it'll be an Etch-a-Sketch type of thing. We can just send this off and print it, and we can start to test it. I think what I'm going to do is I'm going to get... I used to have these big... I got to go find them. But, like, wood boards. And we're gonna screw it down, I think. You can always unscrew it. It's not the end of the world. Just so that we have a big place to, like, test it. And we do want to write some of the software for... Yeah, You need to write like a calibration script of like drawing on the platform what its bounding box is. The problem is we also, I guess, need to calculate the max travel before it starts skipping, because we're not going to be doing closed loop feedback for probably a while. I don't, if ever. So we're going to need to figure out from the point of contact from there. If we were to take, oops, let's not make anything. If we were to take this and this. Okay, but that doesn't mean anything. I guess then the question is, we want the distance from when this thing makes first contact to when this makes contact with this, I believe. Let's just move it over and see. Oh no, it's before that. Wait, is it? I guess it is. Okay. Right. Okay, so to there. So I guess we could take the min distance and add the diameter. So take the min distance along whichever dimension, whichever axes, from there to here. So this surface and this surface have a min dist of 46. Let me just write that down. And then diameter of this is equals min dist from x-axis limb switch to opposite collide point. I don't know. Limb switch roller diam is equal to 4.62. Okay, so what am I trying to use that for, though? What I'm trying to say is that then we should be able to take the distance from here to the distance to here, which is 306. So let's just... So this is 306 flat. We should be able to then take that and subtract 46.1 plus 4.62, which is what? 306 minus 46.1 plus 4.62. Okay, so we should get... So that's basically our travel. I believe that that should be the travel. Was it exactly 255? No, 0.28. Okay. So we could figure out the max number of steps. Okay, so let's actually make a to-do list. So we need to mount to board, calibrate all the settings. Calibrate all the settings in GRBL. Attach the no Z pen holder. And then we need to let's see, I guess so we got to reprint both of those parts. Then I'm wondering if we should use a different type of pen. Because if you use a Sharpie doesn't have a roller, so there's no option for the thing to roll. So we might want to use a standard pen. But, well, I guess actually, if you were to put 2 holes here for mounting, and then you just made this diameter quite big, you could hold kind of whatever pen you wanted because you have 2 points of contact so it can't rotate. So maybe that's kind of the move. I mean, you have to choose the line somewhere. But let's make it 15. So we gotta... Okay. So... Well, no, you know what? Let's just print this. I think we should just print this because... Alright, so let's take this and we're going to export this. And then pen holder. We need to export pen holder. Okay, now we just want to print this out. Bamboo Studio. So we... Oh, is that global? I think we can avoid that one. Yeah. Let's try to disable it for okay. 30 minutes, that's not bad. And do you need to print with the printer door open? I've never done that ever. I've never even seen that before. Okay. All right. Well, that's nice. Ugh. Um. Okay, so now I feel like that's sort of in the pipeline. We can start to figure out how we maybe want to raise and lower this thing. I think that this whole design is actually pretty good. We basically just need to have a way of having this slide up and down on this this part. I'm wondering if I can make like a T slot, like a dovetailed type of 3D printed thing. Like a dovetailed thing. Because really, I mean, if you think about it, we only need like 10 millimeters of travel. We really don't need that much. Okay. You got to make a decision. And I think the decision I'm going to make right now, I do kind of like. There's a huge advantage of using the freaking servo, man. There's a huge advantage of just having a servo and a belt. I really like that design. That's the one that DIY machines did. It makes a ton of sense. There's a couple of reasons why the belt plus servo. First off, servo definitely. Okay, servo super light. That's the biggest thing. Servo is super light. Even this, um, somewhere I have like a real nice. Oh, maybe it's in my motors thing. Huh. I don't know. Yeah, it's light, and I guess he didn't want to put it over here because of cable reasons. Because you'd probably want to run it down this way and then run it across. And then you need a little place for a zip tie or some, even tape, maybe. But it's got to be out of the way of the belt. Actually, I want to look up Onshape belt. Kind of cool.
Sometimes you might design a component that needs a belt, and I will illustrate how to create this belt in Onshape. Okay, let me just hide the present belt.
Dude, I gotta be honest. I feel like, is this gonna be a custom feature or not? Oh, it is.
Okay, let me just hide the present belt. Assume these are the pulleys, this part, this part. Assume these are pulleys. Let me just give them an appearance for ease of visibility. This one's supposed to rotate using a belt. How do you go about it? You just go to the, use this belt here.
Where did he get that? Is that a thing? Yeah, what are you talking
You can see
about?
once you select, you hover at the belt, you can see some documentation here. Therefore, for the pulley faces is this face. I want my belt to pass through this face. Remember the order is very important. Width, maybe I want to use 15, thickness of 2 mm. Okay. Okay. Let me first eliminate the first last two. Then you need a midi plane to select, so that you need to define a midi plane by which to define the thickness. This thickness will be defined from the midi plane. Therefore, I have this plane already created here, plane P1. Otherwise, you can create your plane from this point to this point. Your plane P2, this is the midi plane
Oh,
that I'm going to use
okay.
here. Like that, this plane. You can see a belt is formed, but I want this face to go the other way. You can see here. Just use flipped pulley face, it's like this face, like that. If you want it to go around like that. Okay.
That's cool.
That's how you form a belt. You design a belt in context of the part studio. Assuming now maybe you have an assembly and you want to create your belt using different parts. Right now I'm using the same part studio. Assume now you have different parts from different documents, like that. Let me just hide this belt here, another one here. Assume we need a belt here. Assume these parts they are from different parts studio. This one.
I'm sure that like bamboo and these people actually put in CAD the belt. Like, why would you leave it out? Should we do it? Dude, we should totally do this. Where is it? The belt feature script. Dude, I really... Okay, maybe we should go really... We should level up. Because the wiring would be so good to do. I wonder how many people have even done... Clearly a lot of people have done this, but... There we go. Make a copy. Add custom features to your toolbar. Okay. So that means that I should be able to do it, right? The thing is... Wait, hold on. The thing that's not really that helpful about this... The thing that's not really that helpful about this is that it has to be a closed curve, which is not really what we want. Did I model the teeth on these? No, I didn't. Because I didn't care to. But, let's just stay focused. How do we want to make this thing move, slide up and down? I've never really done a dovetail design. We could build a little test part and see what kind of... So the idea would be like under this. So, okay, so there's a dovetail here and here. So then you slide the pen holder in and now it's free floating. It's going to fall down. And maybe you end the dovetail here at this is at its lowest point. You still have the thumb screw, so you can always adjust. So the dovetail ends. Okay. What does that look like? I'm trying to picture what that looks like. So let me just like draw a dovetail so that I really understand what it means. Because okay. The dovetail looks like just like a well, let me look up dovetail. I guess that's not what I meant. Oh, well, um it's funny how you yeah, okay. There you go. Oh, so the whole thing could be a big dovetail. Not two, but just one big one. So this thing has, okay, so let me just think about this. So this goes like this, and it comes in like that. And you don't want a friction force here. I know on like a tool post or whatever, you have the dovetail, but then you have a bolt that pushes into it so that they mate, and then they have a high friction and they won't deflect. But we don't really have that constraint here because hopefully that's not an issue. Anyway, so then, okay, but then this part then has a thing that also, so wait, this goes like that. So this also goes like that. And then it goes like this. Okay. But at the bottom, that cutout stops. So when if we were to draw this, let's see. So let's go back to this part, which is, we can close this. So if we were to go here, so how is this? I guess it doesn't matter. All right, so what we would do is we'd sketch on here. We draw a line like this, this, this. It'd be straight, this, and that. So we can kind of get rid of these lines. I guess maybe just for dimensioning, we care about them. So these are going to be equal. Then this, and we'll have to look up dovetail geometry for sure. And then this, and we just want to, oh wait, why is that? Is that true? That if I were to change this point, okay, so I guess, right, I guess that's this, because this must be parallel to that because of the verticality constraint. I get it. So then these are the same angle. I guess a big driving thing would be then the distance. I kind of want to use, I don't know why I have that feeling, but okay. I mean, we can make it kind of as, uh, okay, I don't know. Okay. So, uh-huh. Okay, so we're gonna get rid of those holes. Well, do we want to get rid of the holes or can we leave them? Like, I feel like we could just leave them just, for the time being, basically. Um, okay, anyways, let's just decide on a, so what's changing now? Let's see, wait, hold on. The line from here to here, this thing, this whole thing. Where's the whole? That's the midpoint. Okay. But so we should still be able to change this, but it moves them both, right? Okay, great. And I kind of want to change this. I kind of want to get like a real thick boy. So what's left is just the distance between these 2 points. 15. Okay, so then the idea is, wait, this is a Q. So this gets extruded, remove, and it's going to be, so it's not going to be 20, but it's probably going to be like 17 or something. Right? So this is a dovetail. And I'm kind of Well, this is a new thing, is these kind of angles. I've never really done a design like this. But so then the pen holder will slot in there. We'll have to play around with some tolerances and clearances for sure. Oh, but what we could do is that the pen holder could have a little notch here. I don't know how we're gonna make this work with this. We could just get rid of this feature. Or we could countersink it. Wait, we can't really countersink it because this dimension is really only for fitting the threaded. We need to make this part taller. But honestly, the friction. Okay, so let's just assume that that's not an issue. Then what we could do is have a servo on here, and then the pen holder itself has a little lip, and it just moves it up. The thing is, I don't really know GRBL servo. But how do I use it with the shield? That's the only... Wait, is this all? This is all just normal GRBL stuff, but... Uh... What I'm curious about is we need to figure out... Basically where our shield... I need to go grab the shield. This is a terrible image. Is that the highest resolution, or are they just... Okay. Alright, so we have a servo. I don't really know what pins... I guess there is one problem that I can see with this dovetail. Where is it? So let's say we have a lip on the pen holder that goes over, and then there's a servo here with a little horn that is under it. It's gonna be actually kind of have to be a little bit tall, so maybe it's like up here, and then the servo horn is like this. If you lift this up too high, it gets in a. If you lift it up too high, it's gonna drop back down, and it's not gonna be able to get back into position. So it's kind of like a. But honestly, we just want to try it. We want to just try something that works. So we're going to dovetail the dovetail pen holder. We are going to have to sacrifice the servo and install longer cables on it. Then we need to figure out GRBL servo. Especially with the shield. Wait, am I dumb as hell? Yeah, I'm dumb as hell. There's no requirement on that. So why don't we make it as big as we can? And we also need to, okay, we need to look back at this sketch. So I said it was 15. So this was 5. This was 15. And instead of defining it based on an angle, let's define this based on a distance. And let's make this like 20. Yeah, so what is the so okay, can we look and see if there's a video just on dovetail geometry? Dude, BitLooney is so sick. Dude, look at that, bro. Just normal freaking, what are those called? Wing nuts? Anyways, let's look up dovetail geometry. Ugh, it's all wood. Anyone ever talks about is, but I want like metal, like steel or something. $45 degrees. All right, that makes sense. So let's keep it at 45 degrees then. So where is it? So let's just keep it at 45 degrees. I think that makes sense. So we're just going to put that back on there. Keep it simple. Why make it harder than it needs to be? Okay. So, and then this is going to be 45. And so, okay, let's just add it to the pen holder. So we know what it needs to be now. So now we need to do a sketch on this face. And it's going to have to be slightly smaller, right? Let's just get the geometry down. So it's going to be like here, here, here. It's just going to be the inverse of the other one. Okay, there. Is this vertical? Yeah. So then that means that if we change this angle, they both change or something. Wait. Make this equal. Move this down. Wait, what just happened? If I made these equal, okay, there we go. Now the distance between this and this, we're gonna say it's not 15. It's got to be like 15 minus, and let's just say point 0.4. 0.4 is kind of aggressive, but you know. Anyways, then we're gonna draw a line from the midpoint of this thing out. This is gonna be a construction line, and this whole line are gonna be the mid. At this point and this line are gonna be midpoint. Okay. Then the angle between this and this is going to be 45 as well. But I am interested in... so wait, what did we make? So wait, where is... Okay, this is the 14.6. So then that should persist throughout the entire design, right? But I am wondering... Maybe we just add the fillet after. Okay, so let's just get this party started here. I'm wondering... I'm pretty sure if I try to extrude this... Oh no, I guess it works. We want it to be an ad. We need to flip it. Okay, and it works. So I'm pretty sure it's 20. It's kind of a weird design because we left this in there. And actually what we're gonna have to do is we're gonna extend it. We're gonna extend. Well, this part is symmetric about that. So what we could do is, all right, let's redo the extrude, but we're gonna make it like 40, I guess. So then when you, so let's fix the assembly. So we're now gonna, right, wait, I totally messed this up. Hold on. Let's undo this mate. This is this. Let's delete this. So this is freewheeling, dealing. Wait, this is 15, right? So then how is this so much bigger? All right, we need to fix some geometry for sure. Wait, why isn't there a constraint on... Hold on. What is going on right now? 14.6. I'm gonna take this and this. 15. Put the distance between this and this is 10. And the distance between this and this is 5. So we messed something up for sure. Delete this. This is 45. This is 14.6. How did we do the midpoint constraint on the dovetail on this part? Oh, I actually did the dimension. Okay. Oh, okay. So wait, so let's just draw it out. So we're going to say distance from here to here is 5. Do we want it to be 5? Well, we'll try it. Okay, and then we want to... Wait, this should not be fully constrained, though. Oh, I must have gotten some weird... I need a line from here to here. This is going to be a Q. Here and here. See, why is that the case? I feel like something's odd. Wait, undo. Try it one more time, just to be safe. See, what? There's some weird thing going on here. Can we just draw it again? Alright, well, I'll be good at it now. Alright, so we're gonna sketch on here. Okay, I don't really know what just happened, but that's okay. Alright. Very good. Now we're gonna extrude this, flip it, add 40 or something. Real tall. Okay, I'm pretty sure that's the right geometry now. How do we do the mate, though? Dovetail mate. I think I know how to do it. So we're gonna go to this. Okay. And we need to mate that to that, but it needs to be a slider mate, and then it needs to be, so it's not that. Okay, so we didn't do this right. So cancel. So what we're trying to do is we're trying to mate or actually we're trying to mate, I think, that to that. There we go. We just need to flip this. No. Yeah, flip this. Oh yeah, there you go. And it's a slider. So it's gonna wait, how do we preview? Yeah, so that's no good. What if we just try to edit the joints there? Instead of that, it's this. Instead of that, it's this. Then we okay. But we should be able to. Okay, there we go. Nice. Cool. So it's gonna bottom out like right there. Ooh, I'm getting laggy. What the heck? Lagging, bro. And then we're just gonna have a notch here. So, you know, whatever it is, 17 millimeters up. Well, no, wait. We want the notch somewhere. I guess now it's time to start to incorporate the servo. And I kind of hate servos, honestly. But I'm sure we'll be able to figure it out. I think DIY machines use the same shield as me, so it's all good. Um, are we getting close to something that might work? The only the only thing next is going to be adding like a little housing here where we can put a small spring. So, I mean, we could even just do some. That's the great thing about 3D printed parts. You can just do weird geometry. I mean, like I could just put one spring somewhere. And what that would do is that would press. No, that would press this up. We want the opposite force. We want. Oh, we would want like a tower that goes on top of this and pushes that down. I'm just thinking about the future. Obviously, the first model, dude, I'm in the fucking pocket right now. Oh, and the parts is almost done. Well, we're gonna get to do a test, man. That's gonna be cool. I'm gonna get my camera and we're gonna set this up here. I have to clean off a bunch of stuff, but we'll figure it out. I think I might just put it in a big box. Uh-huh. Okay. I think this is gonna work. I think we're gonna have something workable by the end of the day. I'm not ending the stream until I actually can paint like a smiley face, I think. Oh, well, if that's the case, then we need to do a lot of stuff because we need to. Well, we'll get there. All right, so we're gonna be doing the first test. I think I'm gonna make the smoothie now. I haven't had breakfast. And then we'll assemble. We'll put it on the board. I gotta go find the boards. Okay, there is a plan. Okay, so here are the parts. We'll have to get rid of the supports. Actually, not so bad. Dude, support generation has gotten so good, man. It's kind of crazy because support generation, that just seems like a really hard thing. Hmm. There's still some stuck in there. Okay, so this part is good, except I need something. Let's see, how did I get this out before? Damn, this is actually the worst one. Oh, actually, though, I just realized what kind of sucks about this. If we, if I want to test, I'm wondering, hmm, yeah, what I probably should have done is, I think I'm gonna do a little test. Well, the problem is if I use self-tapping screws are not the worst idea here. All right. The thing is, can you? Because typically I've done self-tapping where you actually do have like a hole of some sort. But all right, I'm gonna make some food and then we can figure this out. So I'm gonna mute this thing. I've been reading this book called The Vital Question. And it's about the origin of life, and it's going over like what Luca, the last common ancestor of common life on Earth, might have looked like, and it's just going through. But I was thinking, if you take the set of genes in Archaea and the set of genes in Prokaryote, and you take their union to try to figure out what Luca might have looked like, you're not guaranteed that that set of genes is everything. Like there could be a variety of genes that just went away as maybe prokaryote and and archaea diverged, right? So, anyways, just something to think about. Um, and also, these people doing like virtual cell. Please tell me that they're modeling like what they should be trying to model is not. I don't know. I just feel like it doesn't make sense to try to model the eukaryotic cell. What even is this? Comprehensive platform for modeling cell biological systems. Anyways, what I would be curious about doing is doing differential equation models of Luca. Because, I mean, to try to model the eukaryote, you're trying to jump ahead 4 billion years of evolution and be like, we'll just do this. But it's probably so much more helpful to start, you know. Oh, I found it. Okay. I am going to keep it on, but I'm out of here. Okay, wait, you guys know what I gotta do. You know what's up. Terminal, bruh. Uh, it's always so hard, but oh, why is it not in source? It should be in whatever. Um, wait, what's the changes? Oh yeah, it's so sick. What was this? This was Roam streaming. Yeah. Oh wait, this is in process in AV. Okay, and then we want to do model Luca. Model Luca. Oh yeah, also download a ton of genomes. Iteratively refine them to figure out which genes are the most conserved. I guess it's like DIY phylogeny. Okay, wow, that's smart that's crazy that I knew it was, okay, and then, oh yeah, and I want to build, RPi thing that, detects fire with low error and triggers a fire extinguisher. Dude, that's such a simple thing. Again, a bunch of good stuff. Yeah, right? Like, what even is the. What's the type of software that takes a set of genomes and then builds a phylogenetic tree? Conserved regions. It'd be interesting to look at these. Okay, so it would be interesting to like really do genome analysis, like a real data science genomes. Like, what are the most common edits, and can you use the fact, can you be smarter about recognizing pattern changes and rewrites? Yeah, it's basically like finding um, a probabilistic rewrite system, and you can use that to like reverse engineer, like, because that gives you more information about whether or not just doing the inverse problem of figuring out what the most likely. And the thing is, I'm still thinking eukaryote and sex is like two, is like that there's an actual tree. But I know for bacteria now, I just learned this, that you can't. Bacteria, dude. Also, bro, this shit is crazy. What the hell? Dude, horizontal gene. Dude, see, okay, this is the crazy thing about this book, too. It's like Nick Lane presents this view of how can we understand life? How can we develop therapeutics for humans if we don't start with the origin of life? Okay, but he hasn't. Well, maybe he does talk about virology, but it does not make sense to like leave viruses out of the picture, considering the immune system. The immune system probably developed relatively early in life's history, I would guess. But it is interesting to think about, like, when did life, at what point did it start to be a competition? I mean, because it seems like that is sort of the driving pressures, like properties. Is there a properties? Hold on. Okay. In 2016, genetically analyzed 6.1 million coding genes and protein clusters from sequenced prokaryotic genomes. Okay. Representing many trees. and identified 355 protein clusters that were probably common to Luca. The results of their analysis are highly specific, though debated. They depict Luca as anaerobic CO2 fixing, H2 hydrogen gas dependent. Oh, dude, dude, I love reading books because it's like it's such a mystery. I'm right about to read the part about the acetyl-CoA pathway. Very cool. N2 fixing and thermophilic. Luca's biochemistry was replete with iron sulfide clusters, transition metals, flavins. Oh, interesting. Okay. See, this is highly specific already. It's like to model all of this, you're already like kind of. It's already a big model for. Oh, dude, this picture's sweet. Also, that vent is that's not the right type of vent. I think that's the wrong vent. Are there pictures of these alkaline deep sea vents? I think that this is no, but specifically the alkaline ones that don't. Well, I guess they lump it all into the same thing, but it's not the ones that are billowing, I think. Those ones are too hot. Oh, sick. Oh, it's Nick Lane. Dude, this is exactly what I'm talking about. All right, anyways, regardless, it seems like the biochemistry is the same. Okay, let's just think about this. What do you need? What do you need? Can we get that down? You need uh uh energy in the form of a proton pump. You at least need to be able to make proteins. Where does the lipid come from? I guess the lipid just comes from. No, that would be crazy. Does the membrane code happen naturally, or did it start off with the um is it believed that Luca, the last universal common ancestor, uh had the genes that coded, or I guess the machinery to create its own membrane, or is it more believed that the membrane formed just based on the biochemistry of hydrothermal vents? It is widely believed that Luca lived in hydrothermal vent environments such as where natural proton gradients. Right, you got to think about that. Natural proton gradients. Dude, I'm gonna have to read this book twice. It's so dense, and I'm so like not like I gotta think about it for like a lot more time before it really sinks in. What is good? Because you got to put all these pieces together, right? These percolating vents, and I guess there's somehow a proton membrane that was already there. But that's actually crazy to think about. That's actually crazy to think about the idea that if it's true that the first cells, the origin of life, well, of course it didn't, but it's also remarkable that it did, right? It's like they didn't have membranes. The membranes were sort of there already, but then life found a way to adapt itself to staying alive. But like that jump is so crazy. Life didn't start with membranes. It seems likely. It seems surprise. It would be surprising if somehow. Yeah, yeah, yeah. Membranes are just a huge. I need to write those 6 things required for Luca that Nick Lane has in his book, and we'll be cooking. Um, but the fact that it may have evolved um to make membranes is actually crazy. For real, that's crazy. So they're saying Luca had cell division. Oh, you know what? Cell division cell division is just a natural property of the so I mean the fact that it may have evolved cell division too. Oh, we just there's no free will. We're just passing along a wave. That's quite literally what life is. We're just riding a wave because we're just adapting, bro. We're just on one, man. Like we have not we're engineering ourselves so that I mean, I guess eukaryotes are probably way more different, but the fact that it's just naturally going to happen based on the the concentration of lipid bilayers in the thermal vent, it just naturally happens that they have cell division. It's not like a coordinated thing. It's not like, okay, we know this is going to happen. Although it's probably likely that, because I mean, these are the initial conditions of life. So if when you start to model this and how these genes could be rewritten, you can actually tease out like a lot more about how maybe eukaryotes formed, because it's like surely there's a evolutionary pressure that if it's just constantly happening in these deep sea vents that you're dividing, I don't know, because you need DNA replication before okay, I guess the pressure for DNA replication evolutionary maybe came from the fact that cells were just dividing based on the lipid concentration or something like that, but um it's like we're not at the point. Like, when did natural selection start? That's kind of, I mean, it's been there, right? But it's like we're going from no life to life. So it's like what happened in that time that made it so that, I mean, is it just chance? Like it just randomly happened that the biochemistry for like replication. Lucas system environment, including the acetyl-CoA to fix carbon. We need to know more about the biochemistry here, because honestly, you got to get a picture of what's going on. DNA with enzymes to replicate it. Okay, but before DNA replication, I mean, what really came first? I guess the real challenge here in learning this stuff is you really have to get a sense of complexity scale. Like it's like ribosomes uh what is it, like control O? What am I asking? I'm looking for the like where can I find a link to the simplest ribosome genome? Like basically the ribosome that we think Luca had. Wait, RNA? Oh, wait, no, ribosome. Is ribosome made of? It's just wild that it's like the ribosome is like the fucking coolest. I mean, the coolest. The ribosome is nuts.
The job of this mRNA is to carry the gene's message from the DNA out of the nucleus to a ribosome for production of the particular protein that this gene codes for. There can be several million ribosomes in a typical eukaryotic cell. These complex catalytic machines use the mRNA copy of the genetic information.
Dude. This stuff is so cool.
Complex catalytic machines.
It's like we are really just riding a wave. Like this is all just happening. It's not like the fact that we're here is pretty crazy though.
The mRNA copy of the genetic information to assemble amino acid building blocks into the three-dimensional proteins that are essential for life.
See, that's the thing. Okay, AlphaFold must implicitly have a world model of the exit pore of a ribosome. This would be like such a good question. It's like, does AlphaFold have a ribosome world model implicitly learned? Because basically a AI and molecular okay, let me ask Chat. It's always good to just, you have a great idea. It's good to ask. It's like, the most similar thing would be like, Chat GPT has world model, geographical. What was that? Um, what was that paper? I don't think it's world building. I think that's something else. I don't remember what the paper was, to be quite honest. Let's just get rid of this. Anyways, honestly, it's not even that deep of a thing. It's like AI is just a buzzword here, but it's like, look, let's say I were to tell you, hey, man, fold this protein. Fold this protein. Well, the first thing you'd probably look at is you'd look at the exit where this thing is leaving.
Let's see how it works. The ribosome is composed of one large and one small subunit that assemble around the messenger RNA, which then passes through the ribosome like a computer tape. The amino acid building blocks, that's the small glowing red molecules, are carried into the ribosome attached to specific transfer RNAs.
Wait, what? Wait, what are those transfer RNAs? Dude, that's what this is. Dude, there's so much evidence for RNA world. It's crazy. But also, it's like, why were these, like, so understanding transfer RNAs is obviously super important. Because there's got to be, like, how many transfer RNAs are there? Is there one transfer RNA for each amino acid? There's more than 20 transfer RNAs. Leucine has 6 codons. Different tRNAs. The wobble hypothesis explains that the third position of the... So how many are there? So there's 30 to 40 tRNAs. Oh, wow. And then 50 to 100 in eukaryotes. It seems like a detail, though. Is it important? 100 RNAs? Well, okay. But it's good to know that there's more tRNAs than there are amino acids. Alright, so I guess you gotta know that biochemistry, too. I mean, because this is a really simple model. It's just like, this is the connector. I mean, we must have a ton of tRNAs. They must just be floating around the cell like crazy. Like, if you were to estimate based on models of Luca's volume, likely how many amino acids might have been in one cell? Okay. Cytoplasm in modern cells contains... Okay, so just how many? Just tell me. Wait, what? I don't understand this thing at all. Oh, it's just okay. Well, that's fine. Yeah, that's actually smart. So total amino acids, 300,000 to 1.5 million. Hmm. Kind of suspect. Kind of suspect, right? Because it's like, wait, what were we reading? Oh, we were watching the video. Where's that video?
That's the larger green molecules also referred to as tRNA. The small subunit of the ribosome positions the mRNA so that it can be read
Is this a real
in
video?
groups
Or is this like a...
of 3 letters known as a codon. Each codon on the mRNA matches a corresponding anticodon on the base of a transfer RNA molecule.
So, but there's gotta be some sort of suction cup. The ribosome must have some sort of, you know, handshake with the tRNAs to be like, yo, we're buddies. But it's like, how did that even happen? It's like, this is just really a fluke that we had all this biochemistry going around. It's just pretty amazing.
Each codon on the mRNA matches a corresponding anticodon on the base of a transfer RNA molecule.
So wait, so where do the transfer RNAs come from? Does your genome just okay? So okay, why is this hiding from me all the time? So the question is, where do the transfer RNAs come from? Primarily through the transcription of... But it's crazy that transfer RNAs are like... Dude, actually, now that I'm thinking about it, this is like the whole story of like the history of microbiology. It's like people didn't believe RNA world until I guess this generation. And now it's like, oh, if we take RNA world seriously, we're going to look and we're going to find a ton of RNA everywhere. And I guess folding. Oh, okay. The folding of tRNA. That's weird. Because it doesn't, because tRNA, I guess that's how it started. They just kind of fold on their own. tRNAs just kind of fold on their own. Yeah. But honestly, it's like, um, it's like if RNA world is actually a real thing, then DNA shouldn't be, well, I don't know. Because then, okay, before the ribosome, somehow proteins need to get made. All right, I'm gonna go on the run. I feel like we covered a lot of ground here, though. I need to think about this. I want to keep that picture up, though. Where's that awesome picture, man? Well, there's this. I'm gonna keep this up. I keep all the cool shit up, just so people know we're doing some bomb ass shit. Bam. That's gonna do the fucking thing. Okay. Boom. Luca ribosome. All right. I'm gonna. All right, we're back, bro. We're back. And we are getting into Luca. Luca. So I do need to understand this. Oh, I like this so much. Uh, yeah, wait, hold on. So they have a membrane. They have a membrane and a wall. Oh. Okay, so the prokaryotes has a membrane, but it also has a wall. But see, my guess is that there's just no way. I don't know. It seems so. It would. Someone would need to. Yeah. Okay. Dude, let's just open up the ChatGPT app. It's so much better to have the desktop. This just needs to always stay open. It needs to open on startup for sure. But it takes so long to open. It's actually crazy. I don't know why it takes so long to open. It's a total joke. Um, it has to do a full scan of my computer for all documents. That's why. Um, is the common... Wait, hold on. I actually want to go to this one. Is the common belief that the first... Because Luca is probably not the first life. Meaning... Because, like, I sort of interpret Luca in sort of two ways. It's like, one is, yeah, it's the just last common ancestor. But the other sense is I think of it as like the minimal living thing almost. In any case, what are the arguments for and against whether or not I guess Luca had cell wall in addition to a cell membrane? Because I'm trying to read through Nick Lane's book, The Vital Question, and in it, and I don't know if I understood the biochemistry correctly, but he said basically if you have these lipids, which I guess accumulated in alkaline vents in the deep sea, that these lipid molecules with like a, what is it, non-polar head, I forget what it actually is, but was present in those waters, and if they accumulate to high enough concentration, then just based on the geometry and the molecular dynamics, they form a sphere or they form some sort of closed shape. And that if the concentration keeps getting higher, then cell division happens naturally. But it would be surprising in my mind that a cell wall was present also, because then I feel like that requires more coordination. Yeah. Yeah, but this is the crazy thing about origin of life arguments is you can't rely on you can't I don't think you could just rely on natural selection really. Well, it's like cuz what you're working with isn't even alive. I don't know. So what is the cell wall made of? Does the eukaryote all do all Huh. So no. See, that's interesting, right? It lost the cell wall. I guess because when multicellular life started happening, it made the transition from because the cell wall, right? It does provide mechanical stability, all those things. It's like the global inside outside. And so if you're a unicellular organism, then it makes sense that you need a global inside outside. But when you're multicellular, you can specialize. But still wild that it maybe was a trait that was dropped. Um, and plants, it's like who cares? It's like yeah, whatever. There we go. Why didn't I look at this? This is what I was looking for. Oh, okay. I guess I don't even know what I'm looking at. But is it each circle is presumably a wow, that is fucking cool. Um the cell envelope is composed of the cell membrane and the cell wall. The bacterial cell wall differs from that of all other organisms by the presence of peptidoglycan, which is located immediately outside of the cell membrane. Peptidoglycan is made up of a polysaccharide backbone. For real though, what I know I've definitely Googled. No, no, no. There's no way that a sweet tasting is part of the definition. I swear to the chemical definitions that I like. I mean, good, sure, but we need to have a rigorous pattern. I mean, no, both are both qualitative and quantitative, I guess you would call it, are good in order to describe classes of molecules. Um, so what is saccharide then? The term is most common, which is synonym of saccharide. Okay. So it's quite literally just hmm. That's interesting. I never really because now that we're thinking in terms of origin of life, which is like such a helpful way to start thinking about all this. Polysaccharides serve as an energy store and as structural components, cellulose in plants, chitin, whatever, but also I mean, but the thing is, okay, uh just where is this stuff coming from? Once you have natural selection, you can do whatever you want, but before that, right? It could have been a monolayer. But it's like life is so incredible because of its ability to rewrite itself. You know, it's like it's those first living things that just are so insane because it's like you were given this wonderful gift of a monolayer of sugar or what is it? I don't know. It's not sugar. It's amphiphilic molecules. Yeah. So Luca didn't have a cell wall, and that agrees with my own bias. Oh, there you go. Amphipathic. Okay. Why didn't I just? Sometimes you just gotta read the word. It's so helpful to say it out loud. Amphipathic. Amphi though, not ambi. Amphi. What's the etymology of this? Amphi does mean both, and feel. Okay. Oh, pathos. That's crazy. Yeah. Pathos. Feeling. All right. Double feel. That's cool. Okay. So no cell wall. Didn't start with a cell wall for sure. Cytoplasm. I don't know. Cytoplasm maybe like more emergent than anything else. But like over time has learned to regulate its internal biochemistry way better. How does binary fission work? Okay, wait, but if I wanted to do the simplest experiment where I like was able to use amphipathic molecules to have a self-emergent, I basically want to record uh vesicles forming spontaneously, and then as I dial up the concentration of the amphipathic, then cell division is also spontaneous. Dude, look how long it took for that to open. What a joke. What a joke. Um, I gotta pee. I want to do this so badly. I want to know. Okay, for the materials, how good of a just all right. So you've given me a bunch of options. Now take the simplest, cheapest, one, and also for that one, what quality of microscope do I need? Because that is a concern of mine. That's probably the most expensive specialty thing on the bill of materials for this experiment. I have sushi. Whoa, what? That's so funny. I didn't know it was a real thing. How does a pH meter work?
Previously, I explored making eyeglasses and correcting my vision to see clearly. For my next project, I want to go to the next step in the evolution of optics, allow myself to see beyond human sight, to see the unseen, and make a microscope. The invention of the microscope helped revolutionize science and led to the discovery of microorganisms and germ theory, which has helped save countless lives. For some assistance making my microscope, I sought the advice of Max at Foldscope. Foldscope was invented as a cheap and affordable option for microscopes. Made mostly out of paper that costs less than $1 to produce, it allows you to view at 140 times magnification, making it possible to see bacteria and cells. Hi Max, thanks for talking to me. So for my next project, I'm looking to make a microscope from scratch. Compared to a large or expensive microscope you normally see in a classroom or lab, you guys went with a different format with your Foldscope. Can you tell me about that?
The idea behind a microscope is really simple, which is when light hits a boundary, say between air and glass, it bends. and you can use this property to take a small image and make it much larger. So most research microscopes you see are complex microscopes, which use a series of lenses to provide magnification and correct for aberrations. But you can get away with a simpler strategy, which is actually just to use one very small spherical lens, and this is called a simple microscope. And so the smaller the lens, the sharper light is bent when it crosses the boundary between air and glass, and the more magnification you get. So, for instance, with foldscope is 2.38 millimeters in diameter and provides 140x magnification. And so these simple microscopes are actually really similar to microscopes that were made by a Dutch draper named Antony van Leeuwenhoek back in the 17th century. But Van Leeuwenhoek used the same principle as us, which is actually to use just a simple small lens. So Antony van Leeuwenhoek actually discovered many microorganisms just by looking at pond water using his simple microscope, and is kind of considered the sort of founder of microbiology.
So what exactly goes into making a microscope like yours?
If you think about it, there's not too many things you need to do, right? You need to be able to hold a sample in place and provide magnification with that lens. But then most of the other functions besides the lens can be provided by paper. And so we use a folded sheet of paper to hold the lens and hold the slide and then to align the two. And it turns out that paper, if you think about, you can actually get very reproducibly precise structures out of that. And then the other important thing is to be able to adjust the focus by changing the distance between the lens and whatever sample you have. And one way we do with the foldscope is to have the lens attached to a piece of paper that flexes. And so you can use your thumbs to actually stretch or pull this piece of paper with the lens, and that's how you can focus.
That's really amazing. I think a design like yours would really well for my project.
Awesome. Yeah, well, if you'd like, we can send you a sample of the foldscope if you'd like to use that as a template.
Yeah, that'd be really great. Thanks for your help with that.
Yeah, of course, my pleasure. Good luck with everything.
Thanks to Mac's advice, I now have an idea of what I need to do to make my microscope. But first, I need to overcome the problems I had last time when I made my glass from scratch, which resulted in less than clear glass. The key 3 ingredients I used for glass last time were sand, limestone, and potash. One of the issues with my first attempt at glass was the likely impurities of my ingredients. Pure potash is a white powder, but the stuff I had last time was more gray-green color, so I needed to give this a second try. Once again, I used hardwood ashes to extract the potash from. However, rather than burning a ton of wood this time, just for the ashes, I worked with a nearby restaurant, Doolittle's Wood-Fired Grill, who was able to provide me with a large supply of their leftover ashes. Same as last time, I'll soak the ashes in water and evaporate the potash from the water solution. However, this time to reduce any... Same as last time, I'll soak the ashes in water and evaporate the potash from the water solution.
That's cigarettes?
However, this time to reduce any chance of other stray chemicals that might get concentrated from the tap water, I use only distilled water. Once soaked, I use a strainer to remove the charcoal and other trash that floated on the surface. That's not charcoal.
That sounds like it sucks.
Clean liquid for the course of several hours, I boiled. On the surface was a nearly completely clear liquid that I then slowly evaporated and crystallized. That amounts of iron in the sand that I collected. This resulted in a bluish tint to my glass. This time, I tried using a strong magnet to extract any trace iron. After several passes through, I was able to extract a surprisingly decent amount of magnetic debris, which I think I'll save for a future project. Now knowing that you can extract iron this way, it's very likely you'll be seeing this again in a future episode. Instead of using limestone this time, I thought I'd try a different source of the same chemical, eggs. I've collected a variety of different eggs so far in my quest, and all bird eggs are at least the 95% calcium carbonate that I'm after. So I thought I'd give this source a try. With new, more pure sources for all of my ingredients, it's time to melt them into glass. But you put it on a brick, get it the right temperature. Suspect that this will be, and knowing to mix it, we're getting pretty close. I attempted to pull stranded glass to make the lens from, which I then let cool overnight before the next step. The next step to actually making my microscope lens is to pull a thin strand of glass and then melt it into a bead. To practice, I used some glass rods. Heating them to the melting point under a propane torch, I pulled them until they were super thin and then broke off.
Wait, what?
I attempted to pull stranded glass to make the lens from, which I then let cool overnight before the next step. The next step to actually making my microscope lens is to pull a thin strand of glass and then melt it into a bead. To practice, I used some glass rods. Heating them to the melting point under a propane torch, I pulled them until they were super thin and then broke off one end. Then I heated that end until it started to form a bead. The surface tension of the glass helped it to form into a sphere, and then once it's reached the desired size, I remove it from the flame and snap it off. I have to be careful though, because if it goes flying, there's no way I'll be able to find it. After several attempts and a few different size lenses, I gave the glass that I actually made a shot. With a few different options for lenses, now I just need to make a body of the microscope. Thanks to foldscope, I know the paper can make a great body, which I just happened to have already made when I previously attempted to make a book.
Dude, he's so good.
Cotton paper, I traveled to a cotton farm in Texas where I hand-picked my own cotton. Then I used a gin to remove the seeds from the rest of the fiber. The fiber was then ran through a beater machine to break it up into smaller bits. Then it was placed into a tub of water and a mold was pulled through it, forming the sheet of paper. Lastly, it's pressed in a vise, and then hung to dry. Thanks to the example foldscope sent me, I'm able to use it as a pattern to make mine. Now, I just need to put everything together. And try it with my actual glass. So yeah, that's completely opaque. So in the end, this attempt to make glass was not any more successful than my last, unfortunately. The biggest culprit I suspect of this one was the kiln itself. I think if we could have made it hotter and longer, we would have gotten much better results. However, now it's developed a yellow tint, which I'm not sure why this happened, but there's a chance it might be from trace amounts of sulfur in the eggshells, which can cause a yellow tint to glass. So despite all this, I still haven't managed to make good glass for optics. However, with the glass rods, I was actually able to make pretty good lenses. Hey, it actually works pretty good. I can definitely see the paramecium. Wow, that worked a lot better than I thought it would. I can actually see the paramecium in this slide, which the paramecium is the original microorganism that later the book actually discovered and was able to create the theory of microorganisms.
Very cool. But the thing is, um, focus chat, shift escape. Okay. That's actually crazy. That's nuts. Oh, sick. You have a phone mount. Actually, I wonder. Yeah. Wait, hold on. Okay, I think we could make that work. I think we could get that on stream. Hook up my phone to it. I don't know what that oh, that thing's okay. This thing is just like a picture taker thing. Okay. B bang. So we want the 500x. What's up with that phone? It comes with a phone adapter. Dude, this thing seems sick. Alright, I gotta go find our microscope. Maybe I could adapt our microscope, save some money. I don't really get this one. Okay, so honestly, is it even worth trying that Stanford thing or whatever? Yeah, so what's the level up? What is this? Because this looks freaking awesome, man. If you're to go up in price. Oh, see, that's pretty freaking cool, though. Oh, but it's quite literally just a, yeah. The 3 megapixel, probably a supply thing. Right. See, I'm not versed enough as a consumer to know, because this is a precision piece of equipment, you know? So it's like, I just don't know. Does this thing have a light at the bottom of it? I guess it does have a light. I guess they all need a backlight. Dude, I kind of want this one. It's $100. It's so cheap. And look at that phone thing. I don't know if we'll have to 3D print a new phone thing. All right, so I got to look into how to adapt the microscope that we've had forever, because it's probably enough magnification. I don't know. Maybe it only I think mine actually might only go up to 200x. So what are we doing? We want to see this thing happen, right? So we need to get oleic acid. Oleic acid. The thing is, if I decide to do this, I need a chemicals cabinet. How does a digital pH meter work? Pretty cool. Wow. But it's just for water. See, I don't know if you can just do that. I guess water. I guess it's fine. The thing that annoys me so much about these devices is they're not networked. They don't have IoT and logging. Which, if I want to build a lab, I'm obviously gonna go into it knowing that a lot of stuff is gonna be manual. But if I can minimize that by just making some good decisions about data logging, so that I can just go boop, and then it like uploads it to my cloud notebook type of thing. Anyways, we could just get the strips. The strips are so easy. Um, but yeah, again, super manual. Okay. So what? So the next thing is oleic acid. Dude, buying chemicals off Amazon is so fucking sus. It's just like, what the hell? Wait, are they owned by Merck? Oh. Wait, but which Merck? The German Merck. Not to be confused with Merck. It's just like, what? Merck, not to be confused with Merck. Anyways, so it's the German Merck. Are they the same guy? Oh. Yeah, sort of. All right, well, I don't care. Ligma Baldrich, huh? But probably we can get this stuff will eat your freaking finger, right? Don't you have to be really careful with it? We're a family-owned industrial chemical producer. I really want my chemical producer to be family-owned. So, okay, yeah, they have a ton of products. What is that, the test type or something? What's the cheapest? What if I literally do... Okay, so that helps. It's not as fast as, Oh, wait. How much do you get? You get 25 milliliters? Dude, that's such a joke. Cell culture. 1 gram? Dude, such a joke. Yeah, I'm buying the sus stuff off Amazon. Wait, this is a super small bottle, actually. It's like obviously a photoshopped bottle. What the fuck? There's no way that that's right. Maybe it is, but that just doesn't seem right. Eight ounces? That's so much more than this one. Why is this one in poly bottle? What is poly bottle? I don't know if this is the cheapest one, though. spontaneous vesic yeah.
Under the proper conditions of concentration and pH, fatty acid micelles may join together to form a vesicle. Individual micelles first join to create a large, sheet-like bilayer. Random fluctuations of the fatty acid bilayer lead to the formation of a cup-like shape.
Hmm.
When in close proximity, the ends of the sheet can seal together, forming a spherical vesicle.
So what are the biophysical properties of these closed-up membranes in the form of vesicles or liposomes? So the most important aspect, and something which is quite different from modern membranes that are based on phospholipids, is that fatty acid vesicles are basically, their formation and existence is controlled by a series of phase transitions. So, and the most important of those depends on the pH of the environment. So at fairly alkaline pHs, the carboxylates of fatty acids are basically fully ionized. And then charge repulsion wants to keep those groups as far apart from each other as possible, while the hydrophobic forces want to keep the hydrophobic tail of the molecule as close together as possible. And the result is the formation of micelles, which are very small aggregates, a few nanometers in size, and composed of roughly 10 to 100 fatty acid molecules. Now, as the pH in the environment gradually drops towards roughly 8.5, which is the point at which half of these carboxylates will be ionized and half protonated, there is a phase transition that results in the spontaneous assembly of bilayer membranes, as you can see here. And because the curvature is much reduced in these much larger aggregates, these are actually stabilized by hydrogen bonding interactions between adjacent charged and ionized carboxylates. Now, as the pH drops even further into the acidic range, all of the carboxylates will become protonated eventually.
Mm-hmm. Why isn't there like a real video of it though? In the math department, but they're doing bio research. When was this posted? But this is clearly a simulation. But still, you know, I mean, it's a simulation, but like, why is that happening? Should I expect to actually? Because I feel like I'll be so disappointed if it doesn't work like that. Dude, these videos are so fucking cool. Whoa. It's so movie. That's very cool. I feel like that just might be a cross section. Is it the full
Okay,
thing?
what about some of the other molecules that we need to build our primitive early cell? We need to have lipid-like molecules, amphiphilic molecules, that can self-assemble into membranes and generate compartments spontaneously. So these are molecules that are amphiphilic. They have one part that likes to be in water and another part that doesn't like to be in water. And the way that those preferences are balanced is by forming membranes in which the nonpolar parts are on the inside and the polar parts of the molecules face out into the water. So it turns out that it's actually, again, very easy to make molecules like that in a variety of different scenarios. In fact, Dave Deemer and his colleagues showed that you can extract molecules from the Murchison meteorite. It's one of these carbonaceous chondrite meteorites that's rich in organic materials. You can extract molecules that will self-assemble into vesicles, as you can see here. So they spontaneously make membrane sheets that close up into small vesicles. Here's another example. This is an experiment that was done to mimic processes going on in interstellar molecular clouds, where you have various gases that have condensed on the surface of silica particles. They're subjected to irradiation by ultraviolet light and ionizing radiation. So if you make ices like that in the laboratory, subject them to ultraviolet radiation, you get a lot of complicated chemistry going on. And then in that vast mix of products, you can extract molecules, which again will form membranes and self-assemble.
The space aliens argument. Nah, but honestly though, it's like, it's very, I never thought about it until now, but it makes so much sense. It makes so much sense why there's such an emphasis on space biology, because you can't rule out the fact that biology may have come from outer space. It had not originated here.
Here is yet another scenario. This is a hydrothermal synthesis done by Bob Hazen and Dave Deemer. Again, in hydrothermal processing, you can grow carbon chains with oxygenated groups such as carboxylates at the end, and these self-assemble into membranes and make many compartments, as you can see in this beautiful image. Okay, so what would be an example of an early Earth environment where something like this could take place? There are a series of experiments from the Simonite lab that suggest that hydrothermal synthesis could happen deep down in regions with high temperature and high pressure on the surface of catalytic minerals such as transition metal sulfides or oxides, and those reactions would basically turn hydrogen and carbon monoxide into fatty acids and related compounds. Okay, so the next
I think I'm gonna take a shower. And then we'll finish up the Z axis stuff. I got a pretty good idea of how it's gonna work. It's gonna be dovetail, and then on the top there's gonna be little something for a spring. I think you could use a bolt, like two things. Bolt holds it somewhat out, but then a servo lifts it up, so there's counter pressure. But then its rest state when there's no force from the servo is pushing the pen down into the page, and then either we just iterate the tuning of like the strength of the spring or whatever, or we like actually make it adjustable. But I don't know.
A couple of weeks ago, I played a game of noughts and crosses, tic-tac-toe, and my opponent was DNA, and the DNA won. How's that possible? How can you play a game against DNA? There are these 9 wells, they represent the game grid, and in each of those wells is a special solution of DNA, and in addition to that, over to one side, there are all these other solutions of DNA that I can choose from. They represent the moves that I can make. The way we set it up is DNA takes the first move and plays the center square. When it's my move, suppose I want to play this square, let's call that square number 4, so I find the solution that represents playing square number 4 on my first move, and I pipette that solution just the right amount into each one of those 9 wells. That's how I tell the DNA in those 9 wells which move I want to make. We then put those 9 wells into a special machine. Eventually, one of those wells starts to glow. Specifically, it starts to fluoresce, and that glowing well tells us which square the DNA has played. And then I choose my next move, I find the right solution, and tell each well, by pipetting that solution, which move I'm making.
I gotta pee. Alright, let's keep up, yeah, this looks good. Or maybe the My Cells animation. But not this one, but this one.
Under the
Seems good to me. It's annoying that this image doesn't have a sense of scale on it.
Proper conditions of concentration and pH.
Dude, this guy does such cool stuff, man. Yeah, wait, so we wanted to just look up, well, first off, let's see, what image do they have for this? This is a nice image. Okay, yeah. Crazy. I am curious about that too. Single-celled life. Wait, photosynthesis? Wait. Oh, this is a little bit of a different... Oh, no, I guess it's not a different picture. This is such a good picture, man. So photosynthesis happened for a long time. Okay, so we wanted to look up a video of... Oh, I forgot to get my, What a legend. His book is so technical, though. All right, let's see if we can work through this. Because I feel like I need some images. Like, I need some images. It'll help me a lot.
This was a wonderful place to give a talk, and I've never given a talk following music like that before. This is a completely new experience for me. That was really a wonderful performance. Thank you very much. Yeah, the Dan Brown of evolutionary biochemistry. Notice the word biochemistry. He didn't say biology. So I kind of feel the need to apologize a little bit because biochemistry is, frankly, not very easy to bring to life for people who aren't already enthusiastic about it. I'm going to have a go, and I'm going to try and tell you, I suppose they're some of my own ideas, not only my ideas, but my way of seeing the question on the origin of life. And it leads into consciousness as well, in things like bacteria. So I know that this organization has an interest in the ethics of molecular biosciences and so on. So I don't know if this is going to challenge the ethics, but I hope that it might lead to something of a debate towards the end. Okay, first thing to say is we will never know how life started on Earth. Even if we invented a time machine and we were able to go back 4 billion years to the origin of life, we could not agree among ourselves as scientists in this field. Where should we go? Should we go into the atmosphere? Should we find a beach? These are stromatolites that you can see. It's actually living rocks, you may say. Should we go down into the depths of the ocean? Scientists who work in the field cannot agree with each other about things as simple, you may say, as that. And if we actually did succeed in agreeing on where to go, and we go there and we find some green slime on a rock, do we know if this is a step en route to the origin of life, or was this some side alley going nowhere in particular? Again, we have no way of knowing. So even if we had a time machine, we still wouldn't be able to answer the question. So you may think it's completely hopeless. Why am I even standing here? Well, we can. We can hope to understand it. That's really what we're trying to do. I don't think there's any likelihood that over the next, say, 5 to 10 years, as some people claim, that we will succeed in producing life in the lab and we'll have cells growing out of some test tube or something. I think we are miles and miles away from doing that. But we can try to understand the kinds of environments, the kind of chemistry going on, and all the steps. We can work out an intellectual framework that will explain how a wet, rocky planet with no life on it whatsoever can give rise to the kind of glorious planet that we live on. How can we even think about that transition? I think we can. And what I'd like to try and get across to you this evening is that we're beginning to have some ideas, at least some people agree with them, some people don't, but I want to try and persuade you that it's not just hand-waving. So, how do we begin to think about it? I would say for the last 50, 60 years or so, the guide to the origin of life has really been chemistry, what chemistry actually works and which chemistry doesn't work so well. And over the last perhaps 15, 20 years, biology has become involved for the first time. And until then, surprisingly, biologists had almost nothing to say on the origin of life. It was dismissed as armchair speculation of the worst kind, not science at all. Whereas the chemists were thinking, okay, here's an interesting challenge in synthetic chemistry. Can we make the nucleotides that make up DNA or RNA? Can we make the sugars? Can we make the lipids to make membranes and so on? It was a valid question in synthetic chemistry, and they've made all of these things. And then you have a little problem about, okay, you put them all together in a pot, and then what happens? It doesn't just kind of congeal into cells and start crawling out. So, there's something missing still. Biology, life itself, is an interesting guide. And what I'm going to try and suggest to you is that it's, in fact, an excellent guide in 3 different areas. Energy, metabolism, which is one of those words that tend to put a lot of people off, but I'll try and explain this as lightly as I can. And then genetic information, genes. Where does information in biology come from? Which I think a lot of people find more interesting than metabolism. On the other hand, it can become quite obscure quite quickly. When you see the two together, it makes much more sense. So before I get going, I'm going to orientate you to those 3 themes. This is, you could think of this as a bacterial cell. You could think of this as the mitochondria inside your own cells. The mitochondria are the power packs inside your cells. And this is what's happening inside you right now. I'll keep this as simple as I can. We're burning glucose. We're breaking it down to an intermediate. Don't need to know the name of it, acetyl-CoA. And we go through this thing called the Krebs cycle. And the Krebs cycle is basically pulling out CO2 and hydrogen. That's all I really want you to get from this. CO2 is we're breathing it out into the atmosphere, contributing our own little bit to global warming. And the hydrogen, well, we're splitting the hydrogen atoms, 2 hydrogen atoms, we're splitting them into their fundamental parts, the electrons and the protons. And we have a current of electrons going to oxygen. That current of electrons, literally pretty much an electric wire inside this membrane, inside this insulated membrane, is powering the extrusion of protons across the membrane. So now we have a lot of protons on this side of the membrane, very few protons on oxygen. That current of their fundamental parts, the electrons and the protons. And we have a current of electrons going to oxygen. That current of electrons, literally pretty much an electric wire inside this membrane, inside this insulated membrane, is powering the extrusion of protons across the membrane. So now we have a lot of protons on this side of the membrane, very few protons on the inside. About 3 orders of magnitude difference, 3 pH units difference. Now, that may not seem like very much. It's about an electrical charge of about 150 to 200 millivolts. But if you were to shrink yourself down to the size of a molecule and stand right next to this membrane there, you would experience an electrical field strength of about 30 million volts per meter. That's equivalent to a bolt of lightning. So this entire surface area of membrane has got an electrical charge equivalent to a bolt of lightning going across it. It's just such a small distance, 5 nanometers, that the actual charge is quite small, but it's quite a field strength. That is powering everything. I'm showing here a protein called the ATP synthase. I'll come back to that later on. ATP is often called the universal energy currency. In other words, it's powering work. But that work doesn't have to be making this ATP, this energy currency, any kind of work. It can power the bacterial flagellum, which will kind of row a bacterium around the place. It can power CO2 fixation, which is what I'll say more about. Okay, so that's how energy works in biology. That's basically it for all cells. It's kind of, there are plenty of variations on that thing, but this is fundamental. All life works that way. It's amazing. Your own cells work that way, bacteria work that way, stuff that you find high up in the atmosphere, on the outside of the space station, or deep down in the bowels of the Earth, in the deep hot biosphere. It's all working that way. It's amazing. So it's universally conserved as the genetic code itself. Okay, this looks exactly the same. It's not. It's the opposite. What I'm showing here is this Krebs cycle going in the opposite direction. I've still got hydrogen and CO2. Think what happens. Normally when the Krebs cycle is spinning, it's pulling out hydrogen and CO2 and it's burning the hydrogen in oxygen. The reverse Krebs cycle, and quite a lot of bacteria work this way, is sucking in hydrogen and CO2 and using the energy of this charged membrane to make them react together to form organic molecules, the Krebs cycle intermediates, they're carboxylic acids. And from them, we make amino acids and sugars and nucleotides, the building blocks of DNA and RNA and lipids for the membranes themselves and so on. So it's not about energy only, it's also about biosynthesis. It's about making the building blocks of life. And this is, again, really deeply conserved in biology. Some of the molecules in that Krebs cycle, not necessarily always as a complete cycle, sometimes more as a linear pathway, but there are 5 molecules in there which are universally conserved across all of life. They are the universal precursors for all of metabolism. This is the starting point for making everything that cells do. And it's all coming from here, and it's powered by the same system. It's just operating in reverse. So it's kind of strange that both metabolism and energy are powered by the same system. There's a tension between which way is it going to go? And in our own bodies, sometimes it's going both ways. And cancer, very often, is working with the Krebs cycle going in the opposite direction, in this reverse direction, making the building blocks to make new cells to power the growth of cancer cells. So that's, in a nutshell, how metabolism is working. And genetic information, I'm going to come back to this in a little more detail later on, but just what I want you to take now is that there are patterns in the genetic code, and these have been known about for 60 years, since the early 1960s, which suggests that there are direct interactions between the codons, which is to say the units within DNA or RNA that codes for an amino acid in a protein, and the amino acid itself. In other words, there's a kind of stickiness, you may say. There are interactions between that particular letter and that particular amino acid. And what that suggests is that the genetic code is not just some random arbitrary assortment, but that if you had a random string of RNA, a random string of letters, then you would have a non-random string of amino acids that in one way or another, and it may be more like this, right? We don't need to specify exactly how that works. The patterns are there anyway. What it suggests is that there are direct interactions between the amino acids and the bases in the genetic code.
Wait, what the fuck? Come on, man.
But that if you had a random string of RNA, a random string of letters, then you would have a non-random string of amino acids that in one way or another, and it may be more like this, right? We don't need to specify exactly how that works. The patterns are there anyway. What it suggests is that there are direct interactions between the amino acids and the bases in the genetic code that code for them. And so a random RNA sequence codes a non-random peptide. If that peptide has function in whatever environment it may be, then natural selection as we know it can start. And there's no mystery about the origin of
I gotta listen to that one.
60s. In a nutshell, direct how metabolism is working. And genetic information, I'm going to come back to this in a little more detail later on, but just what I want you to take now is that there are patterns in the genetic code, and these have been known about for 60 years, since the early 1960s, which suggests that there are direct interactions between the codons, which is to say the units within DNA or RNA that codes for an amino acid in a protein, and the amino acid itself. In other words, there's a kind of stickiness, you may say. There are interactions between that particular letter and that particular amino acid. And what that suggests is that the genetic code is not just some random arbitrary assortment, but that if you had a random string of RNA, a random string of letters, then you would have a non-random string of amino acids that in one way or another, and it may be more like this, right? We don't need to specify
I don't really get that.
exactly how that works. The patterns are there anyway. What it suggests is that there are direct interactions between the amino acids and the bases in the genetic code that code for them. And so a random RNA sequence codes a non-random peptide. If that peptide has function in whatever environment it may be, then natural selection as we know it can start. And there's no mystery about the origin of information in biology. So one thing to say about that immediately, what I'm suggesting here is that we have electricity driving metabolism, which is giving rise to genes, and that means it's all got to happen in one place, and that's already a little bit unnerving if you're thinking about the origin of life. Most theories on the origin of life
he's right. It does make sense that the start is not information, but just energy.
So now I've said, okay, well, this chemistry happens best over here, and that chemistry works over there, and this works down here, and we can bring them all together somehow, and then they will, as I say, congeal into cells and crawl out of the test tube. No, they don't do that. So what do? Well, in some kind of a place where we've got a continuous reactivity, continuous gases being brought together, let's say hydrogen and CO2, to react together to form these molecules, forming genes in the same place. It's a scary hypothesis, but at least it's testable, and you could say it's very easily testable because you can do it, if you can get the right conditions, you can do it on a lab bench. If it's all happening in the same place, then you can just go straight ahead and test it. So what kind of place could it possibly be? Well, the place I favour, it doesn't have to be here, but this is something that we can get our head around, are what are known as alkaline hydrothermal vents. They were discovered by Deb Kelly, who was captain of the Alvin submersible back in the year 2000. And before that, there have been other deep-sea hydrothermal vents known back into the 1970s. But these are quite different. They're not smoking in the way that you'll mostly be familiar, I'm sure, with the idea of black smokers with a chimney and smoke coming out of the top, billowing out of the top. They're not like that. They almost look dead. They're not dead. These are living vent systems with fluids going through them. And Deb Kelly here has got a lump of a black smoker with this chimney structure. And this is a bit of Lost City. And you may be able to see it looks a bit like a mineralized sponge. It's a kind of a labyrinth of interconnected pores. And so there are alkaline fluids, hydrothermal fluids, kind of winding their way through these interconnected pores. Now, they're not produced by the same mechanism that makes the black smoke events. The black smokers are produced by effectively direct interaction between magma, volcanic magma, and ocean water at the spreading centres of the mid-ocean ridges and so on. What's happening here, where we're away from this, and water will effectively percolate down into the sea floor. And if the sea floor is relatively close to the mantle, and this tends to happen these days close to the ridges, this is 15, 20 kilometres away from the mid-Atlantic ridge, these green minerals here, it's called olivine, it's actually the most common mineral in the Earth's mantle. It's also extremely common in interstellar space. It's called olivine just because it looks a bit like olives. It's really that simple. And its water, it will percolate down as much as 5 or 6 kilometres underneath the seafloor and react with this olivine. And it's an exothermic reaction. It's releasing heat. And it's releasing these alkaline fluids, so they're warm and they're buoyant and they bubble back up, and plenty of hydrogen gas. And it's basically just the oxidation of water that's going on. Sorry, the oxidation of iron. So ferrous iron is going to ferric iron, and water is being converted into hydrogen. These same kind of vents should form on any wet, rocky planet. And they happen on a global scale. So this is if this is the mid-Atlantic ridge, will be somewhere around here. We have these reactions going on in the crust, and then now with tectonic spreading, it's spreading across the ocean floor and then being subducted down. In effect, what's happening is the water is reacting with the rock and hydrating the rock, and then this hydrated rock is being subducted, and at the increasing temperatures and pressures, water is being driven off again. And that water in the mantle is melting the mantle and causing convection currents in the mantle, and that is driving volcanic activity on the planet, on literally a planetary scale. So it's quite interesting that Mars, for example, which is a fairly small planet, there's plenty of evidence that it had oceans 4 billion years ago, maybe 3.5 billion years ago on Mars, and they disappeared. And there's various explanations for where they went, but one interesting explanation is this same process of called serpentinization, whereby the rock, the minerals like olivine react with water, get subducted down, but on a smaller planet which is cooling faster, the temperatures are cooler now because the core is cooling down, less of that water is driven off, and effectively Mars buried its oceans as rock, as hydrated rock. And that's one of the reasons why Mars effectively seems to have died as a planet. Maybe there's still life hanging on there, who knows, we'll find out. But it would be, to me, quite surprising if there was, and certainly it's not had any real impact on the atmosphere. Occasionally we see traces of methane. Methane could also be produced by this process of serpentinization. Incidentally, I didn't define serpentinization. It sounds a bit intimidating. I say minerals like olivine are reacting with water and effectively rusting, and they're being converted into another mineral called serpentinite, and that's the process of serpentinization. It's a metamorphosis. Why is it called serpentinite? Because it looks like a serpent's scales. Again, the geologists have got these intimidating terms that just mean something very simple. We have a rock that looks like olives converted into a rock that looks like serpent's scales. It's called serpentinization, and it happens throughout the universe. This is Enceladus, which is one of the moons of Saturn. And there are these plumes that were initially seen by Cassini on its fly past of Saturn. And these are alkaline. They're around about pH 9. They're rich in hydrogen and methane and plenty of organic molecules in there. So the interpretation of this is beneath the frozen surface of Enceladus, there is a liquid ocean. And beneath that liquid ocean, there is a rocky, olivine-rich, I don't know what you call it really, not exactly a mantle. I'm not sure, I'm not a geologist what the term would be, but anyway, olivine-rich rock underneath the ocean. Serpentinizing, giving rise to this alkaline ocean, and the pressure is producing these plumes through cracks in the ice. This idea of planetary scale things going on, this is not a very exact analogy, but it's a very interesting analogy. The structure of a cell, the topological structure of a cell and the topological structure of a planet are very similar to each other. So if this is the Earth, for example, the inside has a negative charge relative to the outside. All of the iron, which is buried down in the core, is effectively electron-rich, whereas the atmosphere, the oceans, and so on are relatively electron-poor. We have gases like carbon dioxide and so on. It's relatively oxidized outside. So it's also relatively more acidic outside. This is slightly more problematic. But
that's a little too crazy, actually. The fractal nature of life, it's like, yeah, what the hell?
If you see these as hydrothermal vents between the mantle and the ocean, then we have alkaline fluids coming out, going into a relatively acidic.
See, I needed a video like this that was like, with pictures.
Now, cell structure is basically, it's the same. It's negatively charged inside, it's relatively reduced inside, plenty of electrons and protons on the outside. So at a slightly hand-wavy level, there is an interesting topological equivalence between planets like the Earth, like rocky planets, and the structure of cells. And this was first noticed, really, I don't know if it's first noticed, but it was noticed and pointed out by a guy called Mike Russell 30 years ago now. And after the discovery of Lost City by Deb Kelly, his ideas became quite well known. He predicted the existence of events like Lost City 10 years before their discovery, and his ideas throughout the 90s were pretty marginal in the field. Nobody was very interested in them, and you can look back at conference proceedings and see the discussions after people's talks, and there would be Mike Russell jumping up and saying, yeah, but what about alkaline hydrothermal vents? And everybody would ignore him, and it was quite interesting to see this dynamic all written up in volumes of forgotten life science history.
That's cool.
Then after the discovery of Lost City, he suddenly became much more famous. This was a feature article by Nature in the year 2009, and they photoshopped him up as Erasmus, as the Renaissance man. And they called him Naissance Man, Naissance as in the birth of life. And this is his reactor. He was at the Jet Propulsion Laboratory in Pasadena, and this is a little bit of Lost City behind him. And essentially what he was arguing, and what I still think to be the right way of seeing the question, is that there are high concentrations of hydrogen in these alkaline fluids bubbling up into the ocean. And the early oceans were CO2 rich. It's very hard to constrain how much, but probably as much as 1 bar of carbon dioxide in those early oceans. They would have been mildly acidic, perhaps pH 5 or 6. And that means this is the sponge-like, mineralized sponge-like structure, all of these interconnected micropores. 4 billion years ago, before there was any oxygen, this is now carbonate rocks, but we would expect to see lots of iron and nickel and transition metals in there as well, because these dissolved in the oceans before there was any oxygen around, especially in acidic oceans. So we would expect to see some of these walls effectively containing catalytic transition metals and equivalents. And so reactive fluids percolating, wending their way through, ocean waters coming in. This is really an electrochemical flow reactor where we've got the two components that I was saying earlier on make up the Krebs cycle, or the first starting point for life, hydrogen and CO2, being forcibly reacted together with natural proton gradients, which is to say differences in the proton concentration between the ocean waters and the alkaline fluids, probably across these barriers across potentially quite short distances. So we've got a system here which has a structure which is reminiscent of cells, and we've got all the right ingredients to be reacting together to make the components of cells. So at least you can imagine that this may be a suitable starting point for life. So this is my hypothesis, which is grounded in the work of the people that I've been talking about, but I'm not sure any of them would necessarily see it quite this way, and I wouldn't have dared to show anybody this slide even 5 or 6 years ago. It's very simple, and I'll explain it briefly, but it's, I wouldn't have dared to say it because there's big claims going on here, and they're experimentally tractable questions, and the reason I dare to show it you now is that a lot of them are beginning to show signs that there's truth in them. So imagine this is a pore in one of these hydrothermal vents. We've got acidic ocean waters percolating in. We've got iron sulfur minerals in these barriers, not just that, so silicate and carbonate and things as well, but some iron sulfur minerals, driving a reaction between hydrogen and CO2, not necessarily a complete Krebs cycle, but at least some of these intermediates in the Krebs cycle, to make the most thermodynamically favored products. Lipids, which is to say fatty acids, fat and long-chain hydrocarbons, and amino acids. These are the two most thermodynamically favored groups. If we did make lipids, we potentially would expect that they would form some kind of I'm going to call it a protocell. It's got a bilayer membrane around it, and it's snuggling in. I'm showing it deliberately snuggling into a pore here. I'm exaggerating. But this pore is templating a cell. And the cell is snuggling in with a bilayer membrane around it. And now it's a semi-closed system, and we can make more things, not just lipids.
He said bilayer. Interesting that it's bilayer.
Nucleotides. For this to be happening, we need that bit. This iron-sulfur mineral. Well, if we want to be fixing these things inside a protocell, then this needs to be sticking in this membrane. Protons need to be crossing that membrane. We need to have all this happening inside in a continuous flow. So we're combining the structure of the vent with the continuous flow of things. And this, I hope, will be beginning to challenge you, because certainly I would be thinking, well, really? Can we really believe that that's true? And then just as a final challenge, if we can get as far as nucleotides, then we can begin to have RNA. We can begin to have a kind of an RNA world, but inside these growing protocells. And now we've got amino acids becoming peptides. We've got RNA, which is the kind of more reactive equivalent of DNA, if you're not so familiar with these things. And the beginnings of making proteins, the beginnings of information, and the beginnings of real protein function.
Yeah, so it probably wasn't... Transfer RNA is probably a little bit newer. And that there is just some affinity between nucleotides and amino acids.
Cells. So it's a very simple hypothesis, and it really challenges our ability to believe our own hypotheses in science. But the good thing is it is eminently testable. So I'm going to run through, and I'm going to show you a little bit of data with some of this, and I kind of apologize for that because it's not supposed to be a seminar, but at the same time, if I just stand here and wave my arms around and say, yeah, take it from me, it's really going to happen, you really should not believe me. So I'm going to show you that we can do some experiments, that this is actually science, and I'll show you the kind of experiments that we can do. I'm going to skim over them quite lightly, and if you've got questions, feel free to either interrupt and ask as I'm going along, or ask at the end. Anyway, so this idea that life is powered by electric membranes, it goes back to 1961, to a paper from Peter Mitchell in 1961 on what he called the chemiosmotic hypothesis. And this is an older picture, and it's with Jennifer Moyle. And Jennifer Moyle, she was working with Mitchell from 1947. This is 1947 in Cambridge. And she was a brilliant experimentalist. And most of the good papers that they wrote together in the 1960s on the chemiosmotic hypothesis, the best papers were Mitchell and Moyle together. And she did all the experimental work. Mitchell was a brilliant theoretician. He was cack-handed in the lab. He could never finish an experiment. It was Moyle that really did the experimental work. And Mitchell, of course, perhaps you don't know, but Mitchell in 1978 was awarded the Nobel Prize for chemistry by himself. I'm increasingly thinking, and I've been kind of digging around in the literature, but I think now, if that were to happen, then Moyle would have won the Nobel Prize with him. I think, luckily, times are changing, but I think that was a miscarriage of justice. Anyway, before this hypothesis was first published in 1961, Mitchell was at a conference in Moscow, 1957, on the origin of life. It was organized by Oparin, who was a great Soviet, well, I suppose he was a chemist, interested in the origin of life. And a lot of the great scientists in the world at the time, so people like J.B.S. Haldane was there, and Mitchell himself was there as well, and J.D. Bernal was there. A lot of them were communists, which was why they went to Moscow and why they were interested. But it's also interesting that because there's such a materialistic basis to Marxism and communism, they were interested in questions like the origin of life in a way that many other people weren't at the time. So, there's a reason why it was happening in Moscow. So Mitchell
Wow,
really
dude, he's got a lot of
was not
history. That's
not
crazy.
a communist really at all. In fact, he was from a very wealthy family, and he used to drive a silver Rolls Royce around Cambridge during the war time. And this is quite a poetic view here. I love this quote because it's eye-opening when you think about the origin of life. He says, "I cannot consider the organism without its environment. From a formal point of view, the two may be regarded as equivalent phases between which dynamic contact is maintained by the membranes that separate and link them." So the inside of a cell and the outside world are equivalent phases. He's not separating life out and saying this is what life is and this is what the environment is. He's conflating them. He's saying they're equivalent to each other, which is a strange thing to say. But if you're thinking about the origin of life, before there is such a thing as a cell that we would recognize, before there is really an organism or a living system, thinking about phases as are equivalent, separated and joined by a membrane is a very productive way of thinking about the question. And this is, to my mind, what we have in a hydrothermal vent. We have a barrier, we have alkaline hydrothermal fluids inside, and we have acidic ocean waters on the outside. And so the topology is equivalent to a bacterial cell. Here's a bacterial cell. We're pumping out protons, and so it's relatively acidic on the outside, and it's relatively alkaline on the inside, and potentially it's 3 pH units difference between the inside and the outside. So it's the same magnitude, and it's the same topology as
Wow, some of this really is working
out. Is there any way
out.
that we can kind of go from here to there? The other thing to notice about this, we're pumping out protons all the time in our own body, but why? Because we're putting them to work, to power work. And so the influx of protons is driving work, and the influx of protons across here could potentially drive work as well. What kind of work could it potentially do? Before there are any enzymes, any genes, any kind of structures that you would think could do anything useful, what on earth could it actually do? Well, there is a simple answer. And it's about driving growth. Why would that happen? The problem with hydrogen and CO2 is they're just not very reactive. The first couple of steps to get them to react is really difficult. And so if you were to just take a mixture of gases, hydrogen and CO2, and put them in a test tube and heat them up to, say, 50 degrees and shake them up for 500 million years, nothing much is really going to happen. Actually, thermodynamically, you should get cells. Incredibly, you should get cells. They are more thermodynamically favored than just a mixture of hydrogen and CO2. The problem is this first couple of steps to get to formaldehyde is uphill. We don't need to go into the details of redox chemistry. All you really need to notice is it's uphill, and it's quite steeply uphill to get them to react. But that is at the same pH. What we actually have in a hydrothermal vent is the alkaline fluids at pH 11 and the acidic ocean waters, let's say pH 6. And now you can see it's downhill. Why is it downhill? It's quite simple, again, intuitively to understand. Imagine hydrogen gas. It wants to pass its electrons onto something else. That leaves behind the protons, and the protons, well, that's what makes an acid. So,
I honestly have a really hard time understanding that specifically. Why do they want to get rid of their electrons? Isn't hydrogen gas stable?
Rich in protons. If you make those protons in an alkaline environment, they'll immediately react with hydroxide to form water. It's a neutralization reaction. It's extremely rapid. It's thermodynamically favored. It's going to happen instantaneously and release a lot of heat. So it's just a neutralization. If you try to release protons in an acidic environment, well, you're making an acid more acid. That's not really favored in terms of chemistry. So it's going to be much more reactive in an alkaline environment. And CO2, well, it picks up an electron, now it's got a negative charge. If it's in an acidic environment, it can pick up a proton, now it's balanced the charges, now another electron, now another proton, and off we go. We can make it, so it becomes easier, CO2 becomes more reactive in an acidic environment. And so its downhill is going to happen so long as we have hydrogen in one phase at pH 11 and CO2 in a different phase at pH 6, and they're not constantly mixing. They're not just forming the same thing. So that's what we have in these vents. And this is a fairly simple experiment. Actually, we've been building reactors and trying to make these things react for quite a long time, an embarrassingly long time. And it's got smaller and smaller and more controllable. And this is a microfluidic chip. You can see it there as well. Inside this anaerobic glove box. And we have parallel flow, acidic flow with...
that's actually the tough part, is you got to get rid of all the oxygen.
With iron chloride, and alkaline flow with sodium sulfide, and it precipitates very thin barrier. And what we're hoping is that protons, or maybe electrons, we're still not sure which, unbelievably, will cross this barrier and reduce CO2 to make organic molecules. Does it work? Well, yes, it does. It's not hugely impressive, I have to admit. It's taken us a long time even to get to this. This is the kind of thing, if you're not a scientist, then maybe this will help you understand. People get amazingly excited about that. That is formate, which is to say it's the very first step of reacting hydrogen and CO2 to make the very first product. So it's a step in the right direction. And it's sticking up quite a long way above this baseline. Sometimes this baseline is quite lumpy and bumpy, and so this is not a bad peak, really. And so it's proof that it can begin to happen. And over here, this one is acetate, which is 2 carbons joined together. And we've managed to get 3 carbons joined together. And you'll probably be thinking, well, wow, well done. But it's taken us 10 years. It's a bit embarrassing, as I say. Other people have gone much further, but they've very often used higher pressures and all kinds of interesting minerals. This is with very freshly precipitated with just a pH gradient. And if you cut out the pH gradient, it doesn't work. You don't get anything. If you cut out some of the transition metals like nickel, it doesn't work. You don't get anything. So even though it looks incredibly cheap, it is actually quite exciting. It's a proof of concept that a pH gradient across a barrier will drive CO2 fixation and make the organic molecules. And notice acetate, it's actually one of the Krebs cycle. In the reverse Krebs cycle, it's one of the intermediates, one of the universally conserved intermediates. Now, I said other people have done more than we have. We're now talking higher temperatures and higher pressures and things like that, but some people have produced longer chain fatty acids doing that. And they'd done that 20 years ago, actually, not using pH gradients. And we'd taken a selection of these and tried to see, well, if you remember my picture, I was showing you a protocell nestling snugly inside a pore. Well, that requires a bilayer membrane, and that requires something really simple. And so the question was, if we take these fatty acids that have been made and something called fatty alcohols, which are also kind of a long chain of carbons joined together with an alcohol group stuck on the end, do we get things that look like protocells? And the answer is yes. This is cryo-electron microscopy, and it's got a bilayer membrane around an aqueous space inside. These are similar things. This is confocal microscopy. And I think this one is at pH 7, but this one's at pH 12, and these are also at pH 12. So we are able to make them, and they make stable protocells, quite beautiful to look at. When you see them live, as it were, they're moving around and doing interesting things. They're quite dynamic. So yes, and the question there was, well, are they stable in these harsh conditions in a hydrothermal vent at 70 degrees centigrade and pH 9 or 10 or 11, and lots of salt and calcium and magnesium and all the rest of it? And the answer is yes, that has all of those things in. So it is quite easy to make them, it turns out. And this, I'm not going to go through the details here, but this is another thing where scientists get ridiculously excited about, let's say, this little shoulder here. This is what's called UV-vis spectroscopy. And that shoulder is diagnostic of what are called 4Fe4S clusters, which is a kind of little cube of iron and sulfur. And they're found in some of the most important proteins in biology, things like ferredoxin, which are directly doing CO2 fixation in pretty much all cells. These are ancient proteins, and they always contain these little cubes of iron and sulfur. And they're like minerals.
Dude, give me a fucking
break. In the same way as minerals, they form spontaneously. And so this is the kind of the machinery, this is the most simple machinery you could imagine for CO2 fixation, which is becoming biology. And they have a diagnostic shoulder on UV-vis spectroscopy. So as soon as you see this, you think, whoa, we expected that we would mix iron chloride and sodium sulfide and cysteine, the amino acid cysteine, at pH 9, and we'll mix it up. And what I thought we would see would be smaller crystals, big things, but getting smaller, coated in cysteine. That's kind of what I expected to see. I didn't expect to see that. Suddenly we've gone from when you do it without the cysteine, everything goes black. You just form the mineral, you just form iron sulfide minerals, and everything goes black. And when we first started doing these experiments quite a while ago now, the first PhD student I had, she became terribly depressed in the first month or two because every experiment just went black every time. There was nothing that it took a long time to figure out we need alkaline pH, we need all the, but so it's surprisingly long time, and eventually we get through to forming these. It depends on the amount of cysteine that you have, it depends on the concentration of iron, and I won't go through the details of these. Here's what these little clusters look like. That is this that I showed you. This is from my original slide that I showed you. So what I'm saying is it's quite easy to make the bilayer membrane surrounding it, and it's quite easy to make these little clusters of iron and sulfide that are doing CO2 fixation in modern cells. They have exactly the same chemistry, and they will fix CO2. This is formate and this is acetate, and I won't go through the details, but the green one here is just pure water. This is done on an electrode, so there is an electrical potential here as well, but when we have the clusters we get an awful lot more than you get in the absence of the clusters. So again, it does work. We can effectively build this machinery that life uses with the most simple imaginable ingredients. Okay, so that's effectively turning gases into the core molecules of life. What happens next? Well, metabolism. This is a tube map of metabolism, the kind of the London Underground. The remarkable thing about it is that this basic topology is, again, it's conserved across all of life. You don't need to worry about the details, but that map, it's like, imagine that you go to Paris and you look at the underground map in Paris and you find it's exactly the same as the underground map in London. And you go to New York, and it's not the same conceptually, it's got the same stations. It's incredible. Everything is exactly the same. What's happening down these, it's not as if you've just got some kind of flow going down. What's really happening is each of these molecules is converting into another molecule. So this is the line going from pyruvate through to valine, for example, or to alanine. These are molecules being converted into other things. So it's not very equivalent to a tube map in that sense, but it's remarkable that the genes that code for this map, they're not the same. Some of them are the same, but most of them are different in, for example, bacteria and archaea, two of the domains of life. And what that suggests is that this tube map is actually older than the genes. Now, again, that's something of an assertion. But what it suggests then is that a lot of it should happen spontaneously, that we should be able to just do this chemistry.
Dude, that's what I was saying, is you got to know what is just spontaneously happening. Because it's like,
lab without there being any enzymes there, any genetic programming there, nothing. Which should just happen spontaneously in the right environment. And this is just one example showing more or less that. We're starting with, let me just go back a moment, oxaloacetate, which is here, so we're just feeding it this, and we're looking to see if we get aspartate. This is a very difficult reaction and has never been done before. And what we're also seeing, we're seeing alanine and pyruvate and glycine and serine. So
my guess is that these things kind of co-evolve. Evolved is kind of a loose word because you're not co-developed, maybe, and maybe early proteins only had a subset of more thermodynamically favorable amino acids. Just a thought. Because it's like if you're gonna make a lambda calculus of, or some universal computation machine of proteins, it's like we make high-level languages even in the lowest level thing, compound instructions or whatever. I don't know, but it's like, which amino acids are fundamental and you couldn't do anything without them, and which are just convenient.
This is alanine. These are different metal ions that we're using, so I won't spend much time on the details. We're getting not large amounts, but hundreds of micromolar with copper and with ferric iron, but nothing with those. Aspartate is quite hard, but some metal ions do the job. But we're also getting glycine and serine and alanine. And this was on GCMS. This is just what we measured, which means that we've got this flow going through this system. And it's not coming up with other things. It's like the train is following the lines even in the absence of any gene. So it's not much, but it's there. And we've also got through as far as cysteine, for example, so all the way through to here, which is what's binding those iron-sulfur clusters. So this is early days. There's another group in Strasbourg who's done more of this kind of work than we have. They've managed to do pretty much all of the Krebs cycle, pretty much most of this pathway coming down here, and now a lot of sugar. We've also done sugar synthesis coming through to ribose and so on. A lot of this math has been done in the lab in the last 10 years, since 2015, 8 years, and it works. Not everyone's done it under the same conditions. It's not as if we start here and just go whoosh right the way through this whole system. One group does this little bit, another group does that bit, someone else does this bit. But it's interesting that piecing it together, it seems to be spontaneous chemistry. It's a lot harder to try and get flow going through the entire system. That could take years, possibly decades, who knows. But at least it begins to give you a little faith, I would say, that this kind of chemistry is really possible. Think about the early Earth 4 billion years ago. We've got an entire planet covered in hydrothermal vents, covered in these hydrothermal systems. There was no distinction between the crust and the mantle at that time. So these vent systems were everywhere. And how many million years do you want? So the idea that in the scope of a PhD thesis on a bench top in a small lab, which is always struggling to get funded, that we can make all of this stuff happen, of course it's not going to happen. If we can get anything to happen at all, it's a step in a direction. So I think, again, to return to my point at the beginning, intellectually we're beginning to get a feel for how this kind of chemistry might work out. And we're beginning to do the experiments that suggest that it's not completely impossible, it's not utterly improbable. This was showing that we can make uracil, which is one of the letters in RNA and DNA. This is not too many steps, where we start with ammonia and carbonate and aspartate, and we can go right the way through there. This is uracil and orotate as a one-pot synthesis. And when we optimize the conditions, we got about 10 times as much uracil just in these last 3 steps here. And interestingly, those conditions turned out to be 90 degrees centigrade, pH 8.5, 1 molar sodium chloride, so quite similar to alkaline hydrothermal vents. So again, this is just showing that whole pathways can spontaneously happen. And this is an interesting one. This is ATP that I mentioned at the beginning. These days, it's made by this astonishing rotating motor, the ATP synthase, which is this is the membrane here. It's got this literally rotating motor, and
dude, that thing is ATP. So ATP synthase is so cool.
Is one of the most magical molecular machines.
Dude, ATP synthase is so cool.
And it's rotating. This is not really rotating slowly like that. It's going.
It's like 100 revolutions a second. Yeah.
A second, up to fully like that. It's going 200 times revolutions a second, up to 500 revolutions a second. It's extraordinarily fast. And it's it's just phosphorylating ADP to ATP.
It's like so fast.
To ADP. And it's been a big question, well, how do we make ATP then in the absence of a sophisticated protein like that? There are ways of doing it, but this is just showing, again, with ferric iron and water and 2-carbon acetyl phosphate, we get about 15 to 20% yield of ATP. It varies depending on the temperature. Most metal ions didn't work, only ferric iron worked. And we could do it with ATP, but not with the other bases. So why is it the universal energy currency? In part because you can make it in water with ferric iron as a catalyst and acetyl phosphate as a phosphate donor. So it's prebiotic chemistry. It works, and you get specifically ATP. We're not synthesizing ATP all the steps. This is just the last bit of phosphorylating, but it's interesting that it works. Okay, information. And keep an eye on the time. I'm going a little slow. Are you all right? Should we have a music break? I'll keep going for now. So information. This is kind of what you've seen already. This is the pattern of metabolism. I'm talking about pyruvate. These are the Krebs cycle intermediates up here. And it's color-coded. These are all amino acids. And in gray, they all have a G at the first position of the codon. So in DNA and RNA, each amino acid is encoded by 3 letters. It's called the codon. And those 3 letters, in the first one, for glycine, is always a G, and so on. This is when the first letter is an A for adenosine. In blue, it's encoded by cytidine, and in green, it's by a U. And you can see immediately looking at that there's some interesting structure there. That it looks as if the G is very close to CO2 fixation, and the blue ones are much further away. And that is indeed the case. We see a kind of correlation. It's a reasonable correlation, not perfect, but this is the number of steps from CO2 to the amino acid, and it's the shorter distance from G to U. The outlier down here is cysteine, which is that one, which we have reasons why we can explain why that's an outlier, we think. That's the first position of
What was
explain
that?
why that's
Cysteine?
an outlier, we think. We have reasons why we can explain.
I don't really
why
get
that's
why
an
the
outlier,
first
we
position
think.
is even important.
That's the first position of the codon. If we organize this by the first position of the codon, so a G or an A at that first position, or a C or a U, this is the second position of the anticodon, and this is the hydrophobicity. And so the V is valine. It's a very hydrophobic amino acid. And it's encoded, the colour's changed here, unfortunately, this is now an A. So valine is encoded at the second position of the anticodon by an
The hell
A,
is an
which is the
anticodon?
most hydrophobic base. So we have effectively the most hydrophobic base encodes the most hydrophobic amino acid. And here we have aspartate, and it's encoded by a U, which is the most hydrophilic amino acid encoded by the most hydrophilic base. So we see this relationship between how much water-loving or water-hating they are. It suggests they're snuggling up to each other in some way.
Fantastic.
It's less
Great.
strong
That's
if we're further away. If we're looking at C and U, so these were the ones that were further away at the first position, there is a relationship, but it's not very impressive. But these first two, it really does look as if there are direct interactions between amino acids and the bases that code for them. And this is the third position, and this is what's called an inverted codon table. So first of all, most people would think the third position is usually just thought of as redundant. There's not much information in that third position. So where it's white, it is redundant. There can be more than one amino acid encoded there. But where it's coloured, these are not redundant. It's a single amino acid is encoded by that. So you can see immediately that it's not a random patterning. The redundancy itself is not random in the genetic code. And if I just consider one example, so this is glutamate, and it's the same color as aspartate over here. They've both got a G at the first position of the codon. They've both got an A at the second position of the codon. But this glutamate has a purine, and aspartate has a pyrimidine. Now, purines have got 2 rings, they're bigger. Pyrimidines have got a single ring, they're smaller. And it corresponds to the size of the amino acid. So we can predict most of the code on the basis of these interactions. It's kind of circular. We're predicting the code from patterns that are inside the code anyway, so it's, there's some problem here. But we can also test these things. We've done molecular dynamic simulations and an NMR. And I'll just give one example here. So this is the amino acid proline, and we're looking to see how much time does it spend close to each of these bases, A, C, G,
All right,
U.
I feel like I've seen a lot of Yeah. Huh. I'm starting to understand some of this. Organic compounds, meaning organic means it has either a CC or a CH that contain both amino, which is an RNH2, and a carboxylic acid functional group. Okay.
Within about 2 angstroms, so really snuggling up, it's spending a lot of time with the G, and it's not spending so much time with the other bases. G is the one that encodes it at the second position of the anticodon. For arginine, we also get it correct, but there's a lot of overlap here. So it's kind of weak and statistical, but we can predict about 50% of the code on these interactions. And it's interesting, this is our best, this is the one, so here, for example, with proline, we think that it should be with a G, and that's here. So we think G first.
You know what? Okay, this reading here, biophysical interactions underpin the emergence of information in the genetic code.
And so this is the second guess, this is the third one, and this is the worst one. And I've put a ring around the correct base. And they're organized according to hydrophobicity. So these things are very hydrophobic, these things are very hydrophilic, and we get 50% correct, but they're all the hydrophilic end. At the hydrophobic end, we don't do very well. So this molecular dynamic simulations, I'm not really a proper chemist. It's all about the forces between atoms and how strong are hydrophobic interactions, or how strong is charge interactions, over what distance does it operate, and so on. And they're a little bit clunky, and they don't seem to be very good at these hydrophobic ones. We did that with 2 different programs, and we got the same results, more or less. And we got the same thing with NMR as well. NMR also has a problem with hydrophobicity because you can't dissolve hydrophobic amino acids in water at a high concentration, or the bases, and so you don't have a good signal. So it's very messy. It's funny, this is chemistry that people have been doing over decades, and it's still messy. But there is a pattern, and it seems to be supported by the data, and that can explain the origins of information in biology. This is a summary slide of everything I've said, really. We've got a proton gradient across a membrane driving the reaction between hydrogen and CO2 going into a proto metabolism, making amino acids and nucleotides. We're polymerizing the nucleotides to make RNA, polymerizing the amino acids to make peptides.
Oh, I like that picture.
Chemical interactions between them. We've got something like translation going on here, making these things. And we have all kinds of positive feedback loops interacting there, which can make this system increase. I'm not going to go through the details of this, but we can imagine very simple ways in which these amino acids can interact with very small aptamers of RNA. Right. For the last 10 minutes,
Aptamer? What the hell? Bro, what? I've never heard of that before.
Touch on consciousness in bacteria, not in us. And when I say consciousness, let me confess, probably what I'm going to talk about is not what you would understand by consciousness. But the question for me as a biochemist...
Oh, bro. Okay, let me predict what he's going to say, because this is what I was thinking about. This is what I was thinking about consciousness. It's the awareness of the environment, basically. And it's like, okay, can we come up with something that's a better membrane? Help us stay alive.
Long time when
that's what I think.
Understood it is what are feelings in biochemical terms? What we seem to care most about, I think, as humans, and what we're scared about with AI and so on is will it become scarily human? Will it become conscious? Will it start being sentient, have feelings, all of these kind of things? And a lot of people in the AI world are very interested now in, well, what does biology have to say about consciousness? And the answer is, well, not very much. it's been known as the hard problem for quite a long time, and the hard problem, more or less, is why is it that what a feeling of pain or of hunger or thirst or whatever it may be, what actually is that in terms of biochemistry? If a neuron depolarizes, why does it give rise to a feeling of anything at all? Now, in my view, it evolved. But if it evolved, then then natural selection acted on something. And the question is, well, how far back does that go? You can anesthetize all kinds of things. You can anesthetize an amoeba. You can anesthetize bacteria. So whatever it is that anesthetics are doing to consciousness is not only at the level of a central nervous system, it's also at the level of single-celled critters.
Oh, wow,
what's
weird.
happening? What I've been saying about how bacteria, how life started, this structure of cells and the three parts I've been talking about, and especially the electric membranes, what I'm going to put to you is that the electromagnetic fields, electrostatic electromagnetic fields on these membranes give a real-time integrated feedback to a bacterial cell about how they're doing in the world. And I'll explain that to you and why that may lead to the basis for amplifying everything as consciousness. So a real-time integrated feedback on your state in the world, I would say that's how it feels to be right now. And for a bacterial cell, that means, am I good or am I bad? Really not much more than that. It's a kind of little bit of a binary system. So imagine here's a bacterial cell. We got the outside world, and stuff happens in the outside world, and it needs to detect whatever's going on out there and do something. It's a living cell. It's inside, all it's got is the metabolism, all this stuff I've been talking about, all of these billions of reactions every second that's going on inside. There's nothing else in there. It's just chemistry. It's got genes in there, but genes are slow as well. So it's interesting. We've got literally 1 billion reactions a second going on inside here, and somehow they're going to determine what that cell decides it's going to do. So what I've been telling you about is this Krebs cycle, and I'm keeping with the oxidative one here. We're stripping out hydrogen CO2. We've got food coming in, and we're pumping protons across that membrane to generate an electrical charge on the membrane. So this is what I've been setting up all along.
So there's another thing here that, because you might be aware of the electromagnetic field and the voltage or whatever across the cell, but it gets weird when you start to understand that however much hydrogen you pump across is actually going to affect the outside world. And then mediate, like, oh, I should pump less because something's happening, or I don't know.
Have just one Krebs cycle in there. We actually have scores of them, probably thousands of them, all spinning at the same time, potentially at different rates. There's all kinds of things that could be going on. So what is synchronizing that cell at the same rate? To a large extent, it's the charge on the membrane, because all of them are plugged into the membrane, and for them to spin, they've got to push against the same force. And also, that force is powering ATP synthesis, and for a lot of chemistry to happen in the cell, you need ATP, and it needs to be far from equilibrium, which is to say you need that ratio of ATP to ADP to be a similar distance away. So this charge on the membrane is going to be forcing all of the biochemistry of the cell into effectively the same state, the same rate of operating. And you can gauge what that is from the strength of the charge on the membrane. And also, because this is moving charge, it will be generating electromagnetic fields as well. I suspect, but cannot prove to you, that there's a balance between electromagnetic and electrostatic fields that they can pick up on, which gives them an idea of how they're doing in relation to the environment. So it needs to make a kind of a binary decision. Let's imagine it's too hot, or maybe there's toxins there. What are you going to do? Are you going to stay, or are you going to go? Are you going to paddle with your flagellum and move across? It's a two-bit decision, really. You either you stay or you go, one bit. So you need to integrate all this information on your state in the world. Now, it could be that you know it's too hot. What am I going to do? My proteins are beginning to unravel. They're beginning to come undone. I'm going to set off some genes. I'm going to activate some genes and a stress response, which is going to fix my proteins. But it's going to take half an hour before these things are ready. And the proteins, I need to refold them. That's going to take minutes. I can activate but how do I know what I just did? I need to have some idea now about what my predicament is in the outside world. I need to know it's too hot. There has to be some information that this system is giving me about my predicament. I don't know yet, because I just set off a gene response which is doing something, but I don't know which genes I triggered, and I don't know what the problem is. So this is where a feeling is beginning to come in. It's effectively, I think it's too hot, I should move over there, in terms of the fields on the membrane which are telling you the state that you're in. It's integrating all this information on the membrane. So that's what I'm proposing. It's not completely hand-waving. I mean, this, I admit, immediately is the more hand-wavy bit of the talk. I think the origin of life stuff is becoming science. This is still philosophy, perhaps, more than science, but it's an interesting starting point. But there is also some data. So, for example, these are phages, bacteriophages, attacking a bacterium. And it's quite interesting what happens, because lots of bacteria will kill themselves, especially if they're part of a larger colony, a biofilm, for example, or some kind of ocean bloom of bacteria. Why would they do that? Why would a single cell kill itself? Well, the answer
That's
is
actually,
standard
bro,
biology.
that's crazy that it ended up being like a suicide move. But that makes sense.
It's called kin selection, and effectively, if you kill yourself, you also prevent the viruses from making copies of themselves. Then they can't infect the next cell, and so your genes and so
That
on will
is
do
so
better
interesting.
in your relatives. You don't even have to be very closely related to the next cell. You'll be somewhat related, and your genes will do better if you kill yourself. So how do you, if you're in this predicament of being taken down by viruses, how do you kill yourself? The answer is you unplug the membrane. You collapse the membrane potential. That's what you do. That will kill you in seconds. So this is really bacterial death. It's all about the membrane potential, which makes me think, when they paddle, I showed you them paddling around.
That's crazy.
This is proton powered. Again, it's all the behavior that bacteria do, all the import and export of things across that membrane is all powered by that membrane potential. So this is very much the life and death of what bacterial cells are actually doing. Now, this, I think, is the final slide. We are made of more complex cells. We're made of eukaryotic cells. Eukaryotes have lots of mitochondria. These are the same things I've been showing you. These are all individual bacteria that became included in a much larger cell, or it became a larger cell in the end. And they're all doing the same kind of thing, but now they've got to speak to each other. There's different ways they can do that. They can fuse together and fission. There's all kinds of things they do, but somehow they're all together responsible for metabolism. And in a strange way, because when we breathe oxygen, it's going straight here. And when we're digesting food and burning food, it's going straight here. So although this is the interface with the world, really what's happening is going on here. Any problems that we have in relation to the world, we feel them foremost in our mitochondria. And we need to integrate this information across. Across maybe hundreds or thousands of mitochondria, and again, I'm thinking that fields are one way in which this can happen. And then this is a single cell, like an amoeba cell. Then we have multicellular organisms, and now we've got cells to bring together, all with these moving parts inside. And finally, a central nervous system which amplifies all of this. So
I was thinking of the word amplifies, bro. That's
communications
crazy.
between single cells and their interface with the world becoming incorporated into larger cells, incorporated into multicellular organisms, and finally into a central nervous system. This, I'm suggesting, is the substrate which gives rise, in the end, to the complexity of our own consciousness. This is what I've said. Perhaps I don't need to say it again. I feel like I'm running out of time. So what I'm going to say instead is thank you to the guys in my lab who've been working on this. It's pretty brave for them to do it at all. This is, in fact, an old slide. They're holding the Krebs cycle, and I like that so much. It was a birthday present a few years ago that I've kept it. So half these guys have now left my lab, and I've had to put the ones who've joined since then around the outside. I suppose I'll have to change this at some point, but it's a brave thing to do a PhD on the origin of life, and I'm beginning to start thinking about doing experiments on consciousness, which is probably even more foolhardy for them to join me. So I want to thank them especially. Thanks to the funders, and thank you very much for the invitation.
Oh man, what a good video!
Very happy to
That was a great talk. I feel like I have so much more context for the book now. I feel like when I read the book, I'll have a lot more. Anyways, we're gonna switch gears. It's kind of a diatribe on biology, but we are going to move back into and we'll have to do that. A whole bunch of stuff we gotta do. Alright, but we're back to this. I'm gonna make some dinner, make some food, and then we will begin basically Christ. Okay, so the idea is basically just on the surface, you add a little notch there, then you station a servo motor here somehow. We're gonna have to think about how we want to actually attach it. Honestly, hot glue might work. Hot glue might work. But I am gonna go with servo. I think servo makes the most sense because servos, they're light. That's it. It's going to make the software more annoying because we can't just use baseline GRBL, but honestly, it's just software. It's like, whatever. We could figure it out if we want to. Oh, I wonder if you can give an offset. And everything needs a radius, so we kind of want to fill it. At least this. But whatever, we'll figure it out. Okay, so that's what's coming up. It's crazy how little views this video has gotten. My hypothesis is largely a lot of, well, leaving. I don't know. Could be leaving, but not really convinced by that. Maybe it's title plus content misalignment or something like that. Who knows? This could get messy. Smoking up a magazine. That looks interesting. That looks interesting too.
It's the one and only Digo Double G.
I've never heard of this guy. Is it in Italian? Or is it without words? But I don't want to watch something while I eat. I just want to eat in peace. Talk about life. I hope everyone is in the new year doing very cool things. I know 2025 is going to be a fucking peak year for me. I think I watched this. This was trippy. What was in here? Oh, yeah. The brain body connection. That was crazy. I'm gonna go get more seasoning. Smoking up promethazine. You know that what I mean. What is this?
Good afternoon, everyone. So I'm gonna present Nerve Square 2, neural radio frequency radiance fields. It's quite a bit of a mouthful. And I feel really lucky to present after Howard. So lots of concepts are out of the way. Yeah, we've seen it's very useful to have a very accurate propagation model as to how the radio frequency is transmitted in the space. As Howard has just introduced, we can use the accurate path profile to predict downlink, to predict uplink channel using the downlink information. And we can also have many useful applications like indoor localization sensing, as well as 5G beamforming, which requires very accurate channel state information. So in conventional methods, we typically have, firstly, the scene represented by this point clouds, where we can, this can be obtained from, for example, LiDAR, radar, and then we can also have the precision of the transmitter, as well as the ray configuration, the antenna, the type of the antenna, the power of the ray transmission. Then we feed these inputs into the traditional model. What we get out of it is kind of a heat map where we can see how the signal is propagated given the transmission position across the space.
Okay. $15 years ago. Wow. Wow.
Want to see something cool? Well,
No, Jesus. This thing is sick. Okay, so, okay.
today's video is sponsored by PCBWay. More on that later. What's up, everybody? Welcome back to another episode of Modern Hobbyist. I am happy to announce today that I finally have my own CNC machine, and I even built it from scratch. So stick around, and I'll show you how even a noob like me can build a machine like this.
This guy's sick.
Now, I don't have any experience with CNC machines, so rather than designing one from scratch myself, I decided to buy the plans from Ivan Miranda. Ivan's channel is totally bananas, and I love it, so make sure to support him by checking out his channel and subscribing. And in the meantime, maybe subscribe to my channel too, you know? Anyways, that's enough begging for subscribers. let's get started with the build.
Oh yeah, he did make one. But I saw it before I had any experience.
Most of the aluminum extrusions from Misumi already cut to size, which saved me a ton of cutting, and it actually ended up being about the same price. But I did have to cut these little 40mm profiles down to size on my miter saw. It's easy enough to do with the miter saw, but I definitely recommend keeping it down all the way until it stops moving. Otherwise, you might send one of these things flying across your shop. I definitely didn't make that mistake. I just wanted to mention it for your sake.
I gotta get my drill press up and running again. Is he drilling or is he tapping? I think he's tapping. I've never done that before. I never tapped. Why do you need that many? I don't really get it. I mean, I'm only hoping to cut aluminum for sure. So what's up with all those bearings? Where's the carriage? Oh, it's on. Oh, and it has two carriages, I guess. It didn't show, but there's two carriages. Oh, well, it's obvious, yeah. I guess it was tapped. What is that wire? What was that? I wonder how that belt was held in there. Oh, that's a big belt. I can't stand the fucking music. I guess. Oh, that's a smart design. That's such a... Oh my god, I'm so sick of YouTube. YouTube is so bad. There's no API for data or anything. YouTube is just garbage. Anyways, I like that design where you shove it in and then you clamp it down. I don't know what's under there. Is there... Wait, actually, can you... Oh, I guess it just goes and presses directly onto the thing, which is fine. It could tear there. Kind of a point of high stress, maybe. Now I kind of miss the music. Wow, yeah, double rails on everything. That is the way to do it. I like that design. Smoking on promethazine. Wow, and then dual rails. Damn. This is a pretty expensive CNC machine. And then belt to a lead screw. Oh, dude, this design is so good. He's got the big ass bolts, dude. I don't have bolts like that. That's sweet.
All the mechanical stuff should be done, and now all I have left to do is the wiring. But first, a word from today's video sponsor, PCBWay. PCBWay is my go-to manufacturer for all my DIY projects.
Damn, he crimped
tons
his
of different
own
services like CNC machining, 3D printing, sheet metal fabrication, and injection molding. But what I mostly use them for is PCB manufacturing. Now let's get back to the build.
The funny thing is, nobody really cares if you designed it. Well, I guess the Ivan Miranda video has more views, but not like that many more views. So you gotta like enjoy doing it. That's cool that he's got that. So is that tight in there now? What's that for? Seems overkill.
All right, and here it is, folks. Ivan Miranda's Tiny CNC Mark II, this time with a sexy blue and orange color scheme, and my stupid looking face where Ivan's logo used. I did end up having to design a custom control box because I went with a different power supply than Ivan, and I added a relay to control the spindle, as well as a panel mount connector for a Z-Probe. In the end, I was able to get a spindle, as well as a panel mount connector for a Z-Probe.
Dude, that's fucking cool.
In the end, I was able to get about 210 by 325 millimeters out of it, which isn't huge, but it's big enough for a 12 by 6 piece of aluminum stock, which is a pretty common size. Now, as for what I'm actually going to use this machine for,
I don't know, something amazing, I guess.
No, to be honest, the main goal of building this machine was to learn more about building CNC machines so I could eventually design and build a bigger, sturdier CNC machine of my own. So make sure to subscribe so you don't miss any of my future videos. But for now, if you thought this machine was awesome, then make sure to give Ivan Miranda some love.
Wow, what a good video. And giving credit where credit's due. So sick. And once you have it, man,
I'm way better at building these machines than using them, but this doesn't look too bad. I tried a few more things like machining a giant HTT5M pulley out of 20mm thick aluminum, and I tried also some speed machining. This bracketing here took less than 5 minutes, but pushing the envelope has its risks. And it seems that if you fling molten metal through the vacuum hose adapter, it gets stuck. But overall, if you use it like a reasonable human, which it seems that I'm not, it's a great machine. If you're interested in the files for this machine, there is a link in the description. And that's it for this video. Thanks a lot to all my members and Patreons. Thank you.
That's fucking awesome. Dude, we're building some pussy A. Alright. But, that being said, I do want to... We might need to make this taller, because 17 mils of travel is not that much. Also... No, it'll be able to lift it. It'll be able to lift it. Okay, so we just need to get the servos down, make sure that we got the right one, figure out a bracket for it. I think, I don't know what I'm going to do, because maybe I'll add a little hook here, too, so that it goes this way. So it's always at least got, I don't know. We're going to have to figure out something for those cables, because really cables can get in the way and do a lot of damage. And it's like, it's given like file pathing. It's like, I just don't want to deal with it. Something that should clearly be done by something, but I mean, it's important. Okay, so what's the game plan? The game plan is to I'm wondering if I could... Well, it probably won't work. Because if I mount a servo on the edge... It's not going to be long enough unless I make this thing real long, which maybe is fine. All right, let's get down the motors and look for some servos. You gotta lock in. I really gotta lock in. I'm getting tired. I'm thinking maybe this is a thing for tomorrow, but we're not gonna quit this stream until I got the thing, print it. We solder some big old wires onto the servo, test the servo. It's the long road. Okay, we got some work to cut out for us. Smoking on my magazine. Know what I mean. I don't know if I can go jank so jank that I hot glue something. I don't think I can do hot glue. Okay, whatever. Whatever. Okay, let me get them down. This is heavy. Okay, so these are the motors that we have. So I'm thinking just a standard MG995, just the most standard. I have a ton of these. The thing that's kind of a shame, actually, I'm wondering if I can... I'm wondering if I can, design my own horn. Because I don't think I saw any... Well, we might... Well, no, we don't want to use this. Also, I need to figure out what voltage these run on. Well, it's Arduino, so it'll work. That's nice. The thing that kind of sucks is that I bought this high-end one. It came with a bunch of plastic horns, but it came with a real nice metal horn, and it's one-sided too, which is really what I would want. I've never even looked at this thing. It's supposed to be way stronger. Oh, it's waterproof? That's cool. In any case, that's that. We're not going to use that because I think it takes a weird voltage. I think it takes like 13 volts or something, so it's like, then I'd have to regulate it, and it's like, that's not really that convenient. Yeah, so it's really annoying because none of these bags, I remember I used to raid these bags for the self-tapping screws. Kind of hilarious, actually. Because the problem is then it's gonna collide. So then we'd have to like do some weird radial cut. Do some weird radial cut or something or other. So that it doesn't just hit this face. Honestly, Well, I'm kind of curious though. $5.88. $5.89. If we did two smaller than that, so let's just say we did like, I just want to design a weird little part and do a little test. So the thing is, it's going to go over it. Then I'm still going to need to be able to get my soldering iron tip in there while it's over it. That could work. Or actually, fuck it. We're going to try it. It's kind of stupid that they don't have a one-sided horn. It's like, well, you know what? No, let's just think smart. Why am I being so stupid? Why would I design something when I could just break one of these? I'm just going to cut one of these. And then it should not matter. So I'm just going to take, how do I want to cut it? I could go get the Dremel, but it seems like overkill. Let's just take wire cutters. I feel like I can cut some of this stuff off. It's actually pretty hard plastic. I don't know. Smoking on promethazine. Okay, so this isn't working. Why don't I just get a Dremel? Why don't I stop being retarded? I'm put it in the vise, stick it out. It's gonna go like that, and I'm just gonna go around it. It's gonna take me 1 second. I just gotta get a key. Alright, so we're just gonna use the Dremel and cut this off, and then we'll have something that we can put on here that's one-sided, and it'll flip it up. And then I don't have to do some weird jank stuff. Wait, actually, wait, hold on. This one doesn't even work in this. What the hell? There we go. Alright. So literally it's just going to sit on there like this. Okay, whatever. And it's just going to lift that thing up. And the distance from here to here is probably 15 mils. So we... Maybe I'll put like 2 holes. Maybe I'll go like this and it'll seat it. I don't know, but then it has to be higher than it is. And then, I don't know, the travel on this thing. Okay. We'll figure it out. It's not going to be that hard. Smoking on promethazine. Alright, let's lock in. Wait, what the hell am I doing? I need this thing. Okay, successfully cut it off. Now we have this one-sided thing. Now it's time to actually get to the hard work of I'm almost positive, but let's just go to GrabCAD again. Oh, frick. GrabCAD sucks. Oh my god, what the hell? What? Okay. So we got the CAD for that. It's gonna be a pain in the ass. I haven't worked. I honestly don't like servos that much. Not gonna lie. But so then we also gotta cut this thing off. Split them apart, strip them. We kind of want to know. Okay, then we'll have to solder it together. So then we need that screw. Where the hell? Oh, there it is. Okay. Okay. Okay, so what we want to know, we want to import this thing now. Export, extract. Bro, what the fuck? I forgot about this bullshit. You know what? We're gonna do this. I'm not gonna model it, but I am gonna like do the import from here. It's like this. Okay. Cool. Well, that's nice. Great. Okay. So it has none of the... Okay, so hold on. These need to be grouped. Okay. And this needs to be mate revolute. Animate it. Cool. And MG9. Nice. Okay. Just say rename. Okay, cool. Then this, we can fix this. Now we're good. We got this. This can't move. This can't move. This can move. Okay, so now we should be able to import servo. Okay, so let's just say that this is directly on the ground, this face. Then the thickness of this is going to be 20. Nice, not bad. So that means that this thing is going to be at 10. And then, so we want this to be at like 13 highs. All right, let's just try that. So we're going to switch to sketch on here. What the hell just happened? G, like this. This really only needs to be, like 3. Then the distance between, wait, why is this not, oh. This we want to be like, well, no, we want it to be, hold on. This is going to be 13. And we're going to extrude this by, I don't know, 10? 5? How far do we need to do it? Why didn't that, oh, there we go. So that should be good, right? So then we look at, we can close this now. We can look at this. We have this. And the idea is that something would go all around this and push these springs in. But for right now, like, we're just gonna preload it with the hand screw thing. Okay. So let's think about this. We just need what the hell? I hate how this is mounted. I hate mounting on this thing. Maybe I'll go to the back. Both ways suck. Whatever, we're gonna put an L here and we just need to get the size right. So let me just draw it out because it's not like it's hard, it's just that it's a pain in the butt. So smoking up from the you know is what I need. Okay, I don't know where to put papers ever. Because I need to keep looking at that thing, actually. Okay. Okay, so let me just speed run it. Like, we're gonna actually take this, switch to this. I'm gonna go sketch 1. I'm gonna make this 30. Okay, great. Now I don't care as much about interference. Alright, let me open this in a new browser tab. Okay, so the problem with these is the placement stuff. Nine high. Okay, so what I'm saying is that like we want this to be 2 or 3 millimeters out of that. So if we were to just sketch on here, oh, we can't sketch with this on here. It's so annoying. Whatever, we could just copy that geometry. So we're gonna go to this. Well, I'm gonna go to this. How far does that thing extend out? Oh my god, stop. Stop. Why is it in mate mode? I don't want... Why are you like this? Dude, I don't know why it's doing this. Alright. I want to just measure. I don't want to use... what is this? Snap mode? There we go. Okay. So, from here to here is 5. And then 10 more. So this is 15. So, we have... Okay. So we get something like this. This is a Q. It's like that. This point and what the hell? There we go. And this is 10. Nice. Wow, I'm so sick. I don't even know how that happened. That's kind of crazy actually. And so in here then we're gonna have this thing that's probably like 2 millimeters thick. Yeah. So we're gonna have like, I don't know, like this? And this thing moves up or something? So if that's the case, this thing is like, wait, is it gonna be like this? I guess it's gonna be like this. So why don't we just decide then? This we want to be 3 millimeters away. Again, this is like 2.2. We just measured it. And then how long this is, I don't really know. So we'll leave it like that. But this is all construction again. And then we probably can move it this way. So we want it... Do we want it in the middle? We kind of want the tip in the middle. So let's just make this some arbitrary amount. Like, it really doesn't matter. 3.5. Sounds good. And let's just set this to something arbitrary, but I don't really know what it is. Okay, so if that's the case... Well, that's not really something we have a datum on. So what I'm thinking is we need to just pick a spot. Just need to pick a point. That's at the center of the thing. I'm going to say the center of this thing should be 5 away, right? Wait, which point are we actually talking about? We're talking about the centers of the circle of the... Oh, I closed of the servo. Okay, whatever. Which means that this would be 5. Wait, what? Oh, because it's 2.2. Make this fucking 2. Alright. And then this, let's just say, is 5 away. Okay, fine. So that's where the screw, that's the center of the screw. So now we need to figure out from that point. So we actually do kind of want to reopen this thing. And we want to figure out. Dude, this thing, I honestly, I should just take the Dremel to this. This thing is so stupid. I hate this part of that. It makes me only want to use the bottom. Maybe I'll just do 2 on the bottom. But then I'm worried about an interference. I don't know. Alright, so we need to take snap mode, right? If we get the center, there we go. So that point, oh, that didn't even do what I wanted. Okay, so what we want to do is we want to find the thing that says, okay, radius. Radius. Center disk, but I want more information. So it's the X. So it's 14.05 on the X. Okay, fine. So that's it. So that means that we just need to do this. And on the Y, minus 12. Okay, Y minus 12. So we just need to do that. We just need to make some... Okay, because look, the thing is going to be like this. Superimposed right on here. Actually, let's actually insert the thing in. Insert... Oh, wait, no. Insert other documents... Oh, I probably have to do... Okay. I guess that's what it's called. I thought I renamed it. But whatever. And it's gonna be like this. Wait, where did everything else go? Wait, what happened? Oh. No, not that assembly. This. Okay, there we go. I think it's going to be rotated. Actually, is it better the other way? Let's just stick to 1. So we got... So it's... Okay, so wait. We need to go back to that measurement thing, though. There's this and this. And we just chose... And then Y. Oh, fuck. Wait, I misread. This is 14.05. Okay, and then what is Z? Z does not matter. Okay, great. Nice. So, what are we thinking here? I'm thinking it makes sense to... What we're going to do is we're going to have a bracket. There's going to be a hole, and it's just a little L. Just a tiny little L, but it's thick enough to have a... okay, so let's get back to this sketch. Okay, so we have this point. Now we want another point. Oh, it's shift... Okay. It's like this. And it's like... This is going to be the Y. This is 12.08. And then the distance this way is right. Okay, and then the center distance of okay, 48.5. So then that's the center distance as well. So let's get here, and then we're gonna do another point. It's gonna be like this, but the distance between here and here is 48.5. Way too far. What if we make this like... So we'll never be able to use that. But that's fine. That's okay. I'm fine with that for right now. We could, if it really becomes a problem, we can adjust. Okay, great. So now this just tells us where the top of the thing is. So now what we want to do is we want to draw a rectangle and then something that goes up by 5 millimeters. Well, let's figure that out. So it needs to go up by from this face to this face minus some. So that's just a parallel distance of 9 point. Okay, so then if we are doing the side face, we have .5. So we'll just do 9 millimeters. So we need it to be, and let's just have it go to, so if it's like this, we just want it to go up to, let me think. So we are definitely going to have a 4 millimeter thing right here. So this is the center. Oh, and then what's this dimension? From here to here. 7 point, okay, so minus 7. So, and then the distance, like this. So that's min distance centered. There we go. I like that. That's great. Okay, so we can go 4. We should be able to go just 4. So let's just make it 8. Let's make it big as hell. Why not? I think it should be okay. So we want a rectangle like this that is coincident with that for sure. The thing is, this part is going to be a new part. So it needs to be... Okay. So let's do this. Okay. So these are shift midpointed. The distance here is going to be 8. Oh, wow, that's big. Okay. This, we're going to make it 4. Oh, wow, that's big. That's huge. I gotta hate these little bracket pieces, dude. Okay, whatever. This needs to be extruded by 9. But not like that. New part. And just to be sure... Oh, frick. Oh my gosh. Oh, that's 16? Oh, wait, but that's not... Wait, what is it when it's bottomed out? I'm almost positive it's 13. Okay, so what we want to measure is from there to there. Yeah. Okay, so we should be fine with that. Okay, so now we need to... And it's not going to be a mid-plane, so we need to, like, actually look at... We're going to have to refer back to... I don't know what that is. We're going to have to refer back to this sketch quite a lot. And it does not look like we're going to be able to do this. So we need to actually take this... Make this 15. Why don't we just put it in the middle? That'll work. That'll work. Let's just do that. So then let's do... And this is going to be 4. And this is going to be 8. And then this is going to be mid-pointed. Okay. And then... I mean, it's really only one... It's the same part. But I do want to model both of them. Okay, so then... How high up do we need to go? We need to go 5 millimeters up, and we're going to do a... it's going to be a 4.7 millimeter hole. Okay, so... and oh, this is 4, but this is exactly 4. But alright, that's fine. So then we just need to figure out that it needs to be... I'm pretty sure it's centered. I'm almost positive it's centered. And then I'm pretty sure it's... So it needs to be... Okay. Is that right? That's not right. I messed this up. Hold on. Okay. So let's just delete these because I messed this whole thing up. So this needs to be mid-pointed here. So these are... Then we just need to determine... Oh, wait, but I fucked this up. Obviously, I messed this up. So this needs to be 5, right? Well, we'll find out. So let's extrude this. Remove, up to next. Okay. And I can't do a mirror, but I kind of want to apply that exact same sketch and feature to this. I'm wondering if I can do that. What? What the hell? How is that so bad? How is that so bad? That's so bad. Well, whatever. We can use it. This is quite literally... Oh, wow. That's absurd. Okay, so never mind. Literally faster to do this. Which is crazy. Okay. Alright. I should have just copied part and pasted it. I don't know. I don't know. I don't know. I don't know. Let's just do this. Sketch new. Here to here. Let's just make it 2. That should work. And we just need to extrude it by 10. Ugh, I hate that tangency constraint. We gotta get rid of that. Change to driven 2.5. Okay, fix that. All right, so now we need to draw a sketch here, and then we're gonna project it. So, okay, so let's sketch on here. We're just gonna put it in the center. No big deal. I think that we're good on that. This is gonna be M3 hole. We're gonna extrude. Oops. Yeah, it's a circle extrude. Remove up to next. Great, but then we need a sketch on here, and we want to use this so that we get the concentricity, and then we need to be 5 minus 0.3, and we're going to take that. Oops, so wait, let's hide this part. And we're going to take this, and we're going to extrude this. Oh wait, actually, hold on. I'm going to take this and this, remove this, and it's going to be 4. And it's just going to be one. It's just gonna be one bolt. Kind of stupid, but. And what about the? It's gonna be 4 plus 2.6. So even my smallest screws aren't really gonna be up to the task, kind of. But whatever. Let's just delete this part, by the way. I don't know. We got this one part, and then we'll do the rest of the parts. All right, so let's go to this thing. So we have. Whoa, this thing got way off track. Where is it? Oh wait, we have the hole, but it doesn't give me the part. That's actually nice. So then we want to go to tinycnc. This part 2. Oh, and I guess we need to. Oh. What the hell? So never mind. I messed this up. Delete. But I want to just make. I want to replace this part. Can I just replace that part? I don't think it works like that. Oh wait, but I should be able to. I think it's 9. No, it's 10. No, it's 8. I'm pretty sure I should be able to just do this number over. So we're gonna hide this part, sketch on here, circle here, this point. Okay, wait, let's redo this. All right, cool. So we should now be able to, this is technically bad behavior. But, first off, go to, Smoking on promethazine. Let's delete this. Rename this to servo bracket. Okay. We're just trying to get something that works, bro. So now we need to copy this. Wait, we just insert another one. I don't really care. Oops, no. Oh. Okay, great. Where the hell did it go? Okay. So now where's my servo? I thought I inserted a servo. So wait, we need a map. So wait, we want it to be this one goes to there. We did it! Okay, so we have some interference there. So what I'm gonna do is I'm just gonna make this even longer. Smoking on that promethazine. Gosh, you can just tell my design capabilities are like pretty third rate. Okay, I feel like the assembly is gonna be a pain in the ass. All right, so we're just gonna go back to that. Is it this part? I guess it's this part. Go back to sketch 1. Make this thing 35. Oops, 35. And there's just no way that we won't have the clearance now. So we look at full. Come on, update, 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 update. It's time for you to update. Oh, really? Oh, is that because... Oh, because... Okay, so that's not gonna be good. So we need to go back through the sketch... And we need to change... Okay, so I'm gonna leave that change, but then I'm gonna go back to this thing. And we're gonna find sketch 8, I believe. I'm gonna take this, and we're gonna make this... like 8. Just bring it back by 3 mil. We should be good. We do all that. It should everything should be working out. And we could have it pointing this way inward. So we'll have it pointing inward. Wait, okay, let's get it to this way. Right. Oh, I fucking okay. So, I think did we just do it? I think we just did it, man. Now we gotta strip the wire and see if it works. And that's gonna be a tough thing because... Alright, well, let's export the parts and see what we can do. So we're not gonna screw it in. It's gonna be dovetailed. Alright, cool. I think I'm ready, man. Export, export, export. What? And then we need to Jesus. That should be fine. Uh-huh. Is that it? I think that's it. What did it say for time? An hour? Dude, this project is sick.
So I just accidentally figured out how you can use your phone like a microscope for $2. So here I've got two little optical lenses, one connected to a very cheap VGA camera module for Arduino, it costs like $2, and then here I have the same lens removed from the actual PCB. And the first thing I want to demonstrate this with is by zooming into the corners of this torn piece of paper towel. So for a light source, I'm going to be using my 12,000 lumen 100 watt COB LED. And then to diffuse all that light, I'm going to be using this roll of duct tape with a piece of PTFE taped to the top. It may look terrible, but it works. So turning it on, and if it doesn't work, you can dislike the video. So I'm putting my piece of paper towel right on the surface there, followed by the optical lens. Now I'm going to take my phone out of the tripod and show you what it looks like right over top. And remember, this was taken out of a $2 camera module. And just take a look at the detail in a second here, right there. Look at that. And here it is zoomed in. Beautiful. So I just accidentally figured out how you can use your phone.
That's pretty cool. Dude, I don't want to see news ever. All right, I don't know what the hell I'm even doing, man. What did I want to look up? I don't even remember. I'm hoping that we can get this to be low friction. I mean, we're gonna have to find out. I can do the assembly later. All right, this is great stream. Finally got another 8 hours. I mean, honestly, most of today was not doing anything. So, I was gonna look up GRBL servo stuff. Paper clips, that's nice. Wow. Dude, what a sick guy. Who the hell is this? Dude, everyone's built a pen plotter. Everyone's built a pen plotter, man. So he's using the thumb screw idea. How did he attach it? Dude, I love how polished they make these videos, man. I never get anywhere close to this level of polish. Why isn't it working? Whatever. That's what's cool about... Why am I watching this shit?
indicate how many steps the motors should take in order to move 1 millimeter, through which we will send G-codes and tell the machine what to do. The most popular choice for DIY CNC machines is the open source Gerbil firmware. However, for this pen plotter we need a modified version of it, which can control the servo motor. The modified version is called Gerbil Servo, which alters the default PWM frequency of the spindle control.
I mean, if he got it to work,
number 11 from 1
then I'm gonna
to
do
50
it.
Hertz, which is needed for controlling this type of servo motors. Once we download and install this Gerbil firmware into the library folder of our Arduino IDE, we will also need to modify its config.h file in order to enable 3-axis homing instead of its default 2-axis homing, and of course upload Gerbil to the Arduino.
Wait, but he used 3 steppers.
Which is a dedicated
Wait,
software
didn't
for
he?
controlling plot.
Wait, what?
Default 2-axis homing, and of course upload Gerbil to the
Wait,
Arduino.
then why is there... He
As
put
for
a
the
limit
control
switch
software,
on
we
the
will use
Z
Gerbil
too?
plotter, which is a dedicated software for controlling
That's pretty
plotters, and includes
sweet.
a graphic converter through which we can generate input from our images or graphics. This one is also open source, which can be downloaded from GitHub. Here, the first thing that we need to do is to connect our Arduino board to the software through the suitable COM port. Once we click the Q alarm button on the serial monitor, we will get a list of our current Gerbil parameters. We need to change some of these parameters according to our machine. The first thing that we should adjust here is the travel resolution, or the steps per millimeter value. These values indicate how many steps the motors should take in order to move 1 millimeter. This depends on the type of the stepper motor that we have, the selected step resolution, and the motion transmission, in this case the GT2 belt and the pulley. For our machine, a value of 80 steps per millimeter is needed for the X and the Y axis to be accurate. As for the Z axis, I set a value of 40, which is actually not accurate in terms of real motion, but we cannot achieve that anyway with our reciprocating motion. We should also set the parameter number 23 to 0, which describes where our limit switches are located, set the maximum feed rate, acceleration, maximum travel speed, and set the parameter number 1 to a value of 255, which enables the steppers to be active all the time. However, we should note that with this being enabled, especially for the Z-axis stepper, we should adjust the current limit of the driver to minimum, because the shorter NEMA 70 stepper motor can quickly get hot. Nevertheless, for more details about configuring the Gerbil, you can always check the website article, where you can find links to more resources. Okay, so let's take a look at the controller setup now.
I don't even understand that. That is clearly a stepper motor, right? Let's go back to the assembly. Go back to video again.
How I built a CNC pen plotter or a drawing machine, but with one cool feature, and that's automatic tool change. In other words, the machine will be able to automatically change colors, and so we can draw really cool stuff with it. The construction of the machine
he uses the servo for the automatic tool
machine with minimum parts possible. It uses 3 NEMA 17 stepper motors for the X, Y, and the Z axis motion, and a small servo motor for the gripper. The brain of the CNC machine is an Arduino Uno board in combination with a CNC shield and 3 A4988 stepper drivers. The work area is fairly big, 360 by 280 millimeters, and the level of details this plotter can output is, in my opinion, quite impressive too. I was actually surprised how good and precise the drawings came out, especially the ones where I used a 0.6mm gel pen. Nevertheless, now I will explain everything you need to know about building a drawing machine like this, including how to design it, connect electronics, what firmware and software to use, and how to generate G-code for it. To begin with, let's have a look at the design of the CNC machine. As I already mentioned, this machine is based on the design of my previous CNC laser engraver machine, where the goal was to make a very simple CNC with minimum parts possible. The two main components here are these MGN15H linear rails, together with their suitable sliding blocks. The motion for the X and the Y axis is provided through GT2 belts and some GT2 pulleys. As for the Z-axis, we have a simple reciprocating motion, where the moving parts slide up and down on 2 6mm linear rods and suitable linear bearings. A small hobby servo is used for gripping
I like
the pen.
his design.
The holding position is essential for this pen plotter, as the pen holders have a specific fixed position, so the machine must have a starting point. Therefore, we must have a limit switches for each axis. You can find and download this 3D model, as well as the STL files which are used for 3D printing, on the website article. The link is in the video description. So here are all the parts needed for assembling this pen plotter, but before we do that, I would like to thank Surfshark for sponsoring this video and also explain why and how I actually use this service. Within a second of visiting any website, your location, hardware details, operating pave, and 3 bolts. All of the bolts for assembling this machine are actually M3 with various lengths, except for a few M5 bolts needed for the GT2 pulleys. Once we have the two sides ready, we can secure the X-axis linear rail to them with 2 bolts on each side. These MGN15H rails provide very smooth and play-free motion, as their sliding blocks have balls or rollers inside them. However, before installing them, it's a good idea to clean and grease them well in order to work properly. Next, the Y-axis rail should go on top of the X-axis sliding block, and for securing them together, we will use a central mounting plate. First, we can install the Y-axis rail to the central plate using 3 bolts. Then we can install the 2 NEMA 17 stepper motors. One goes on the top side and the other goes at the bottom side of the plate. As I mentioned earlier, we need some M5 bolts and nuts for installing the GT2 pulleys in place. The 2 pulleys here are actually idler pulleys, which are used for providing grip for the X-axis GT2 belt, and the tooth pulley which goes on the stepper motor. As for installing that pulley, we should measure and level it according to the idler pulleys. As for the Y-axis, we only need one idler pulley, which goes on the other side of the rail, as the belt for this axis will be installed in a loop. Okay, next is the marriage, or connecting the two axes together. We simply do that by securing the central plate to the X-axis sliding block using 4 M3 bolts. With this, the machine got its main shape, and now the Y-axis sliding block can reach any position in the work area. We can continue with assembling the pen lifter mechanism. This mechanism is composed of 2 parts, one fixed that's bolted to the Y-axis sliding block, and the other one that will be sliding up and down. Once the fixed part is secured in place, we can install the Z-axis stepper motor on it. This stepper is also an IMA 17, but it's shorter, 23mm instead of 40mm in order to cut on weight. Then we can install the lifter, which is simply attached to the shaft of the stepper. The grab screw that I had was a bit long for it, so I put the lifter to the shaft without it, but its hole has a shape as the shaft, so the motion will be transferred well. I actually ended up modifying this part a little bit, but no worries, you will get the updated version of it in the download files. Next, I inserted the 4 linear bearings into the sliding part and secured the micro servo in place. Then I also secured the pen plotter holder part right next to the servo. For connecting the fixed and the sliding parts together, first we need to pass the servo wire through a hole in the fixed part and then insert the 6mm rods from the top through the bearings and through the fixed part hole. While installing the rod, we should also insert a spring in between the fixed and the sliding part in a way that it pushes the sliding part down. This will help the pen to have a better contact with the work surface. At the bottom side of the fixed part, there are openings where we can insert M3 nuts and use them for securing these 6mm rods in place. Next, we can assemble the pen holder unit that goes on one side of the machine. It's composed of top and a bottom part with openings that can accommodate up to 12 pens. I continued with installing the belts. First, we need to measure how much length we need and cut it approximately to size. For attaching the belt to the sliding block, I made these cool belt connectors where the belt goes around the hollow shaft and in between two holes that doesn't allow the belt to move. Using an M3 bolt, we can secure the first connector on one side of the block and repeat the same procedure for the other side. We can move the connectors along these slots here and so tension the belt as much as we want. As for the x-axis, the belt will go in a straight line from one to the other side while passing through the pulleys in a way that they will provide tension or grip to the stepper motor pulley. For tensioning the x-axis belt, I made these connectors that have a shape as the belt and so we can tie them to the sides of the machine.
That's
Next,
also really
limit
nice.
switches. I actually ended up lowering a bit this Z-axis limit switch, and as for the X and the Y limit switches, I used the ones from my previous project, which already had wires connected to them. With this, the mechanical part of this machine is ready, and now we can move on with connecting the
Dude, see, I
electronics.
need to get better
As I
making
mentioned, we are
nice
using an Arduino
parts,
Uno board
man.
in combination with a CNC shield and 3 A4988 stepper drivers.
My
For
stuff
attaching the
just
Arduino
feels
board
so
to the machine, I made an
junky.
additional 3D printed part that goes on the side panel. I secured the Arduino board with 2 M3 bolts, and on top of it I inserted the CNC shield. Here we need to insert 3 jumpers for each stepper driver in order to select 16 stepper resolution, and then insert the stepper drivers in place. Then we can connect the motors to the CNC appropriately. For connecting the micro limit switches in place, I simply soldered wires directly to them, and on the other side I soldered female pin headers which I got them from some jump wires. As for the servo motor, I used some servo extension cables so that it can reach the CNC shield. For powering the machine, we need 12 volts power supply. Nevertheless, here's a circuit diagram of how everything needs to be connected. There are a few final touches that need 12 volts power supply. Nevertheless,
Is there 5-volt and ground breakout on these things? Where even is it? Oh, it's in the other room. With the Z-axis. What?
here's a circuit diagram of how everything needs to be connected. There are a few final touches that needs to be done in order to complete this pen plotter. Here I'm installing the pen gripper, which is simply attached to the servo motor through the servo horn. For managing the cables from the pen plotter, I used a dining table mat, which material is firm but flexible, so it was perfect for the job. With this, our drawing machine is actually completed. However, there are a few things that we should note here. As the Y-axis rail is unsupported on one side, and the 3D printing PLA material itself is not that rigid, when fully extended, the pen lifter was 4mm lower compared to the supported side. That's way too much play, but I managed to solve that issue by lifting the front side of the machine a little bit. In this way, I reduced the difference to around 1mm, which was acceptable. If you plan to use these big rails, I would definitely suggest to support the Y-axis rail on the other side as well. Another issue is the pen holder, because the pens don't stay in place well in this way. Here I would suggest making the top openings bigger and add some soft material on the sides so that the pens can stay in place while being easy for the machine to insert them. Finally, we can insert a board under the whole machine so that we get a nice and flat surface. And that's it, our machine is completed, but what's left to do now is to give life to it or make it a real CNC machine. For that purpose, we need to install a firmware to the Arduino for controlling the motion of the CNC machine, and we need a control software through which we will send G-codes and tell the machine what to do.
Okay. Dude, this design is awesome. Dude, this design is rad. This thing is sweet, man. It's so simple. Wait, does that thing have feedback? Man, I like that design so much. Wait, what is he doing? What did he do? Okay, wait. Let's go to the go to the other one. And I want to see the part 2.
And a timing belt. In a similar fashion, the y-axis, which goes forward and backwards, is controlled by the stepper motor underneath the platform. The z-axis, which is the...
Is mine under it? Mine's on top, right? No, mine's under it. Yeah. A very weird design.
Moves the pen up and down, is controlled by a small servo connected via a timing belt. The finger dials on the front make it very easy to change the pen without the need for any tools. The Arduino and other electronics for this project are housed in this container, which is kept cool by a small fan. The addition of 2 ports makes it very easy to pack up or move your project elsewhere. If you haven't yet seen part 1 of this video series, which covers the 3D printing and assembly of the machine, then you can find the link to that video up here in the corner. I've also put one in the description below. Now, this video is going to be a little bit more wordier than mine usually are. This is because I'm going to endeavour to show you how to test your machine as we go through each step. This will help you spot any problems before they get buried too deep, and it will give you a better understanding of how exactly your machine works. The first thing that we will need to do is upload Gerbil to our Arduino. Gerbil, which can be pronounced as Gerbil, Gerbil, Garble, or even GRBL, is some free open source software which is used to control CNC machines. It's ideal for our project. However, it is designed to control machines which have a spindle or laser attached to their heads. We will be using a servo in our machine to move our pen up and down, so we're going to run a modified version of this software. This is called MeGerbil. You can find a link to download this software and any of the other software that I talk about during this video in the description below. Download the Gerbil Me folder, unzip it, and then copy it into your Arduino's library folder. On a Mac, this is usually users/yourname/documents/Arduino/libraries. And on a Windows, it's usually something like mydocuments/Arduino/libraries. Open the Arduino IDE, again, links to download this are in the description, and in the menu, go File, Examples, Gerbil Me, Gerbil Upload. Connect your Arduino to your computer using a USB cable. Select the Arduino Uno board type in the Tools menu, and the correct port for your Arduino, and upload the sketch. Once the upload is complete, you can open the serial monitor and set the baud rate to 115200. Sending $2 should return Gerbil's current settings. To begin with, we will upload a set of configuration settings for the design as I have built here and have shown you in the first video. We will use this to check that the motors work properly and that our limit switches are responding as they should as well. I have put a link down in the description to where you can get a copy of these configuration files. Copy and paste the settings line by line into the Arduino serial monitor, and they will automatically apply themselves to your Gerbil installation. You can verify this by sending the double $ signs again to see the current configuration, which should be different to what we saw earlier. As a quick side note, the configuration for Gerbil is saved to some non-volatile memory on board our Arduino. This means that it will be remembered when we power off our Arduino and power it back on later. So don't worry about trying to reload your configuration every time you switch your machine on again. Before we begin testing the hardware, gently and slowly manually move the CNC machine so that the head is roughly in the center of the expected working area. As we have some homing switches configured on our CNC machine, When we first switch it on, it will start up in an alarm state. This is because it cannot be sure at the moment where its head is in relation to the rest of the machine. To resolve this, we will trigger a homing sequence, which will move both the X and Y axes to their very ends until they make contact with the limit switches. These two switches are located here and here. We will issue the homing command to our Arduino in a moment, and what we want to see happen is the axis to move all the way to the left and all the way to the bottom left corner of our drawing area until it engages those two contact switches. At this point, it will perform a small bounce on the two contact switches to improve its accuracy, and then we will read OK in the serial monitor. Be prepared to disconnect the power if your machine does anything other than this. If it does, recommend going back to the part 1 video and checking your work, paying attention to the electronic connections so far. You can also take a look at my website for some FAQs on this project's page to fix some of the most common faults you might come across. If it has worked just fine though, we'll move on to testing the servo's ability to move the pen up and down in its slider. To do this, issue the command M3S90 followed by M5. The servo should pull on the timing belt and raise the slider when M3S90 is issued. This should have lifted the pen slider upwards very near to the end of its travel, and our servo should not be continually straining to try and pull it any further. If it is, refit the timing belt inside the 3D printed arm on our servo, giving it a little bit more slack. As we may have jogged the position of the machine since issuing the first homing command, we issued the
Does this
$H,
have a
and then
spring?
once homed, issue G92X0Y0. This tells the machine that wherever it is now should be known as the origin by setting its current location as 0 on both the X and Y axis. If you would like to move both the X and Y axis manually using Garble, then this is a great way to test how everything is working so far. To do this, we can manually issue the following command: G1, X10, Y50, F2000. Let's break this down. G1 tells it to move
But it
in a
doesn't
linear
really,
fashion,
he doesn't
that is,
really
in a straight
say
line.
like,
The number following X and Y are the coordinates
he doesn't really say about
from the origin in millimeters. And the number after F, which stands for feed rate,
Gerbil
tells the machine
me.
just how fast to move. Now that we know that's working fine, we can set our computer up to automatically feed our Arduino G-code lines so that it's able to draw a much more detailed drawing than we could by issuing commands ourselves. The G-code sender which we will use is a web application called Chili Pepper. Head on over to its website, chilipepper.com/Gerbil.
he just has it here, but
I'd
where is
recommend
this
using Google Chrome for
from,
this.
bro? What the
The
hell?
first thing which we will need to do for Chili Pepper is install a JSON server onto your computer. This is just a small program which helps your web browser connect to your Arduino via the USB port. To do this, follow the download serial port JSON server link in the lower right and download and install the correct version for your operating system. Ensure your Arduino is plugged into your PC before starting the program. Go back to the Chili Pepper window. Reload the serial port list with
Yeah. Okay. Alright, that's it for the stream today. We designed something. We designed some janky parts. Alright, good stuff, good stuff.